Okej, nu kommer synas. Det är fine. Ja. Go live.
Ja, det var ganska dålig årsklass nu. Exakt.
Så jag kollade det. Presentationen var så när det spelas på något så här.
Det kan ju också lyckas.
Det är något passande efternamn så här. Jag fick reda på det här år sedan. Hon heter Annika Vinst. Men Vinst stavas W-I-N-S-T-H. W-I-N-S-T-H.
Okej.
Men jag hörde det på radio först. Jag körde bil och jag satt och lyssnade på radio. Och så sa de så här, ja nu ska vi prata med Norges spelsäkert om Annika Vinst. Jag bara, va? Hur ska vi inte kunna lyssna på
Alltså, det känns som att det är skapat. Det är som allting var
Det heter
John. Det är sant. Vi hade en grundlig utredning.
människor. Det var svårt. Miranda. Är det lite tydligt för det?
Är det bättre att sitta här
Juli och operatör. Ja. Jag kan ta den sidan.
Man ser inget. Alltså när de filmar den är liksom precis.
Det kommer, alltså, det klipper nästan så kommer höras. Jag drog ner det. Ner volymen på liksom klippan för det är faktiskt det börjar klippa.
Och jag kommer stå och fasta här emellan så om ni vill se det vill
ändå ta färdigt. Det gör vi. Ja, faktiskt. Ska vi bara få inte länge Alltså, huvudanledningen jag köpte den, det är för autofokus i rörelse.
Det kan vara en intreplik någonting.
Ja, så är det.
Ja, det är mycket koncept.
Det är många i Stockholm.
Ja.
Det är precis det här. Jag skulle vara mest familj och vänner, familj.
Ja, det var det. Det var också lite vänner och vet att mentorer också.
Ja, det gör det.
Lite mamma här.
Nice.
Men varför vill du läsa 200%? Kan man inte bli väldigt Men Benjamin har jag samma kunskap. Det är bara att Benjamin lyckades klara det på något sätt. Jag förstår inte hur det är. Men Julia läser väl inte 100%?
Jag läser ju, jag är som kandidat i min master i tillämpning. Alltså om du läser civilen på egen data. Ja. Det är väl det här som är bra. Vilket också alla beräkningsfält.
Det beror på vad du beräknar. Men om du gillar beräkningar, varför är det så?
Det är beräkning.
Inte lika mycket som fysikdata.
Men det här kan gärna göra det.
Spännande att höra din presentation. Ja, du köpte. Jag trodde det var annorlunda i schemat. Okej. Ja, men nice. Men då snackar vi lite senare då. Vi snackar lite senare. Ja. Men det kommer jag på. Jag tror det. Det kommer vara jätteintressant. Vi får se.
Det syns mycket, men jag tror inte så mycket.
Hej och varmt välkomna till Rays avslutningspresentationer 2024. Good morning and welcome to Rays final presentations 2024. We're so happy to have all of you here to listen to our students present their research. Before we start, some emergency information. You'll find the emergency exits on both sides of the stage. If anything happens, the assembly point is outside of the main entrance of the Ethnographic Museum, on the other side of the street from the main entrance of the Science and Technology Museum. We also want to share some of the main points of the schedule before we start, so you know what's coming. The presentations will start very soon, and then we'll have a break for lunch at 12. The presentations will start again at 12:45, another break at 2:45, and we expect to be done with the presentations around 4:30. Note that while the presentations will be in English, you're very welcome to ask questions in Swedish as well. But before we start, behind this summer research school, there is of course a team of organizers who make all of this possible. So I would like to welcome to the stage the director of RACE 2024, Olle Lapidus, who wants to say a few words. Welcome, Olle.
Hi. Once again, a warm welcome to the closing presentations of RACE 2024. My name is Olle, and I've had the immense pleasure of directing this year's edition of the Summer Research Camp. 4 weeks ago, 21 high school students came from all across Sweden to Strängnäs because they wanted to devote a substantial part of their summer vacation conducting research at KTH, at KI and at SU. They came with curiosity, with open minds and with a strong passion for their respective fields. And over the course of these 4 weeks, I've gotten to know all of these 21 amazing students, and I've been continuously impressed by their ambition, by how well they take care of each other, by just everything, how amazing they are. And I've had many interesting conversations with them about their cool projects, which they will soon present to all of you. There are a few people I'd like to thank. First of all, I want to thank the other members of the organizing committee, Linnea Jonrad, Solveig Englund and Arman Aspromonti, for enabling this race, for making everything happen, and for all of your work, tremendous amount of work. I want to thank all of the lecturers and former RACE students who came to visit the program and helped broaden the program, make it more interesting, more fun. I want to thank all of the mentors who've taken in these students at KTH, KI and SU and helped them pursue their passions. And finally, I want to thank RACE itself and all of the partners of RACE for enabling all of this to happen. I'm now going to play you a video from one of our partners who wanted to say a few words to you.
Hej, jag heter Cecilia Wikström och jag är VD för Beijerstiftelsen. Och Beijerstiftelsen är stolt huvudsponsor för RACE forskarskola. Ända sedan stiftelsen grundades 1974 så har vi haft som ett uttryckligt mål att stötta unga människor inom forskning, vetenskap, kultur och också utbildning. Att vara sponsor för vetenskap, det innebär att vi bygger framtid. Och ni som har förmånen att tillhöra RACE forskarskola, ni skapar ju framtid tillsammans med era handledare och universitet och högskolor i Sverige och runt om i världen. Det är vi stolta över att kunna bidra till genom era fantastiska sommarskolor. Någon utav RACE forskarstudenter kommer att finna en liten bit av lösning för de riktigt stora samhällsfrågor som vi alla ställer oss. Frågor som handlar om att bota sjukdomar, lösa klimatutmaningen, hitta system som håller när vi bygger hållbara samhällen. Jag hoppas att vi ska kunna tillsammans verka för att samhället och världen blir lite bättre imorgon än den är idag. Och därför så står både mitt och stiftelsens hopp till RACE forskarskola och alla de studenter som får förmånen att gå där. Och jag vill också tacka alla handledare, alla akademiker som bidrar på ett sådant underbart sätt till att den här skolan blir verklighet år efter år. Tack! Hej!
And finally, I want to thank all of you students for being so amazing, for taking care of each other, for having fun together, for devoting all the hours that you've put into making these projects as fantastic as they've become. So thank you.
Okay, it's time to start the actual presentations. First up is Klara Bragesjö-Björkén and Kasper Johansson. Klara studies at P.A. Fogelströms Gymnasium and has also studied more mathematics through Stockholm's Matematiska Cirkel. Kasper has also studied more mathematics, but at Lund University, and usually studies at ProCivitas Helsingborg. They are going to present their project about graph theory. Welcome up, Klara and Kasper.
In the middle of the 19th century, Michael Faraday introduced the concept of field theory. Field theory describes interactions between particles through fields, functions of space and time. Michael Faraday focused on the electromagnetic field, as viewed in this picture. It describes interactions between negatively charged and positively charged particles. Field theory was later developed into what is now called as quantum field theory, combining the classical field theory with quantum mechanics and special relativity. Quantum mechanics describes the interactions of particles at a very small scale, while special relativity describes how objects that move really, really fast, almost at the speed of light, behave. Quantum field theory describes interactions between particles as fields, and these particles are viewed as perturbations of these fields. For instance, the electron is viewed as a perturbation of the electromagnetic field. Quantum field theory also describes the interactions that combine together and form the standard model, which is the foundation of our universe. Particles can also be described through particle physics, and these interactions come in many different forms. There are different types of particles, for instance, fermions, leptons, and bosons. These particles can be studied using what is called as a Feynman diagram. Feynman diagrams show how particles interact with each other, and have one axis showing space and the other one showing time. The lines in these Feynman diagrams can be different. Straight lines represent a certain particle type, and wavy lines or squiggly lines represent another particle type. If we simplify, the Feynman diagrams simply just represent interactions between particles. The lines represent the particles moving, as I mentioned, the actual particles. And then the intersections, or when the interactions happen, like a new particle forming or any other thing. There are many types of Feynman diagrams. For instance, one is called 5-4 Feynman diagram. This diagram describes the interaction between 4 particles. So in the beginning, we have 2 coming in, and then an interaction could be 1 step, could be 100 steps, could be as many as you want. And then at the end, you have 2 particles coming out. So, scientists use these diagrams to study interactions between particles. But how can we generate these diagrams?
It's a very natural question to ask, really, and it is also the aim of our study, to generate these Feynman diagrams as well as counting the number of them. But the natural question is, how do we do this? And the approach we have chosen is to simplify these Feynman diagrams, with a modification of course, into graphs from a branch of mathematics known as graph theory. And then by constructing a recursive algorithm that we then use in our open source algorithm written in Python, we can generate and count and draw all of these diagrams. But let's not get too ahead of ourselves. First of all, what is a graph in a graph theoretical sense? A graph is simply a set of points, known as vertices, and lines connecting these points, known as edges. Here we see an example graph with 5 vertices and 7 edges. A closely related concept to that of a graph is what's known as a multigraph, which is simply just a graph where each pair of vertices can be joined by, instead of just one, multiple edges. We will simply refer to multigraphs as graphs throughout, as most diagrams studied will be multigraphs. There are a few other interesting or important concepts for us to discuss. First of all, the degree of a vertex is simply the amount of edges connected to said vertex. So here the vertex A would, for example, have degree 2, while the vertex B would have a degree 4, as it's connected to four different vertices. Another very important concept is that of a graph isomorphism. Two graphs can briefly be said to be isomorphic if they are the same in the sense that the vertices connect to each other in the same way, if you arrange them properly. So here, for example, the two graphs are isomorphic, as if you rearrange the vertices in the first graph, in the configuration shown in the second, the edges will essentially look the same. Because these graphs are equal in some sort, we can note now that we do not want to generate Feynman diagrams that are isomorphic to each other, because then they represent, well, essentially the same interaction. That's not very interesting to us. But that's not good to have of ourselves again. How do we represent these Feynman diagrams as graphs? Well, if you consider this diagram, we can represent it as a graph by just, instead of treating the points of intersections as, well, simply points of intersections, we treat them as vertices, and by removing the direction of all the particles. But still, this isn't quite a graph, as there are edges going in and out of the entire structure, which we do not allow. So we simply introduce vertices connected to these in and outgoing edges that we call external vertices. And this is a completely satisfactory graph. But of course, there are some more constraints we want on the Feynman graphs. First of all, we do not want any structures like this, known as generalized loops. A generalized loop, broadly speaking, it's a structure that does not have any external edges going in and out of the graph, and that is only connected to the rest of the graph in one vertex. And speaking briefly, diagrams having these loops model interactions that are not actually possible in the physical world. So we simply choose to ignore them. Another structure that we do not want are edges like these, known as cut edges, that divide the graph into two distinct structures. And the reason here is actually much simpler. If you have such a cut edge, then the interaction can be modeled as two separate interactions, instead of one larger interaction. These separate interactions are, of course, much easier to study than the interaction as a whole. And so, we are not interested in these kinds of graphs.
Yeah, so now that we have used to introduce a Feynman graph we want to introduce another concept, called a vacuum graph. A vacuum graph is a connected graph, which means that all of the vertices are connected to each other. So none of them are separate. And additionally, all of them have the same degree, which means that all of them connect to the same amount of vertices. No, the edges. The vertices connect to the same amount of edges. As you can see here, we studied 4 Feynman diagrams, and therefore they connect to 4 edges. And the vacuum graphs can be used to generate Feynman graphs through an operation that we call subtracting a vertex. It consists of removing a vertex, and then removing all the 4 edges connected to it, and then after that, the Feynman graph is constructed by adding 4 external edges and then 4 external vertices. So as you can see here, we go from this vacuum graph to this Feynman graph through operation subtracting a vertex. But how do we create these vacuum graphs? Well, our algorithm is recursive, which means that we manually create the smaller vacuum graphs and then use 2 operations to create the other ones. There exists no vacuum graph with 1 vertex. This is because we don't allow edges to connect between the same vertex. But for 2 vertices, we have 1 vacuum graph. It's simply just 4 edges connecting the 2 vertices. The first operation is called crossing a vertex. It consists of removing 2 edges, adding 1 vertex, and then connecting this vertex to the edges, to the vertices that just have the edges removed. And this operation increases the amount of vertices by 1. The second operation is called tripling an edge. This consists of removing 1 edge, adding 2 new vertices, and connecting these vertices to the rest of the graph, that is more specifically to the vertices that just had their edge removed, and then connecting these vertices together by a triple edge, or simply put 3 edges between these newly created vertices. And the question we now can ask is, can these operations produce all Feynman graphs? The simple answer is yes. If you reverse these operations, you find that by creating all Feynman graphs, you can also create the vacuum graphs by reversing the operations. And since the creation of the vacuum graphs is recursive, it is possible to create all Feynman graphs through these operations.
So we have generated all Feynman graphs with up to 9 vertices, but here we will simply show the Feynman graphs with up to 4 vertices. In these drawings we have also omitted the external vertices, simply for visibility reasons. Here we can see the one Feynman graph with exactly 1 vertex, and here we have the one Feynman graph with 2 vertices. Here we have the 2 Feynman graphs with 3 vertices. Moving on, there are 8 Feynman graphs with 4 vertices, and all of these are shown here. Now, as you can see, the diagrams become more and more complicated as we get more vertices, which isn't strange, as when particles can interact with each other if there are more points of interaction between particles, then we will get more complex interactions, and that is shown and represented in these graphs. And the reason we have not to draw more, actually, is because the number of Feynman graphs with respect to the number of vertices grows really, really fast. If you actually consider the ratio between consecutive numbers of Feynman graphs, you observe that the ratio increases very, very quickly. And this suggests actually that the number of Feynman graphs doesn't just grow exponentially, which would already be really, really fast, but even faster than exponentially, as if it were to grow exponentially, this factor would be constant. So yeah, there are a lot of Feynman graphs when we have a large number of vertices. And this ties into a problem we have actually, is that the algorithm is very slow. We made some good optimization, so it's possible to run the algorithm to still produce for large amounts of vertices, but it's a slow algorithm and it scales upwards very, very quickly. For some context, generating all Feynman graphs with 8 vertices took about 15 to 20 minutes. Generating for 9 Feynman graphs took 6 hours, which is slightly longer. And this is simply a consequence of the fact that the number of Feynman graphs increases so quickly. You need to generate a lot of graphs. To analyze how the time by the algorithm was spent, we actually timed the different parts of the algorithm, or some of the different parts of the algorithms. And what we found was that the check for if the generated Feynman graphs are isomorphic to each other took up a very large portion of the time spent. More precisely, for 9 vertices, this sub-algorithm took up 99.9% of the total time, which is a lot of time. And this is essentially a result of the fact that there is no, in some sense, fast way of finding isomorphisms. Finding the optimal way to check if 2 graphs are isomorphic is actually an unsolved problem in computer science. But that being said, there are faster ways of checking isomorphisms than that we have used, as Clara will get into now.
Yeah, so as Casper just mentioned, finding the optimal algorithm that checks for isomorphism is still an unsolved problem. However, there are special cases. For instance, for vertices with degree 3, graphs that contain this, there is an optimal algorithm, but there is no optimal algorithm for a general case. And therefore, you could continue studying how to generate or create an algorithm that checks for isomorphism way faster than we have checked. For instance, it could be checking for different characteristics. Instead of counting the amount of double edges or triple edges in a graph, you could also check for other characteristics. And another thing that could optimize our algorithm is something called parallelization. This would mean that the operations are being performed at the same time. Normally, the operations are performed one at a time. But through parallelization, you can perform multiple operations at the same time, depending on how fast your computer is and how many operations it can perform at the same time. So if your computer allows, for instance, 12 operations to perform at the same time, the algorithm could run almost 12 times as fast. But of course, not all parts of our algorithm can be performed at the same time, since some of the parts depend on each other. But some parts, like checking for isomorphism after creating the Feynman graphs, can be parallelized. Another thing that you could continue studying is different types of diagrams. For instance, how cool would it be to find an algorithm that creates all possible Feynman graphs, no matter the amount of external edges or how the degrees are in the graph for the vertices. For instance, there could be a graph with degree 7 for the vertices, or degree 8. And additionally, the degrees could also be different. In our case, we chose to only study Feynman graphs with the same degree for all vertices. But you could also study Feynman graphs with different degrees for the vertices. So, in conclusion, our algorithm produces valid time graphs, but it can still significantly be improved. By, for instance, finding a better algorithm that checks for isomorphisms or using parallelization. And it can also be improved by creating more of these time graphs, and not just 5-4 time graphs with degree 4 of the vertices.
Finally, before we finish the presentation, we would like to acknowledge some of the people and organizations who have helped us finish this project. First of all, we'd like to thank our mentor, Sabine Halleby, who is here with us actually right now, for designing and guiding us through this excellent project. It's been a real pleasure working with you. And of course, we would like to thank all the people who have worked on this year's edition of RACE. It's been a truly marvelous 4 weeks. And of course, all of the partners who have financially helped make this project possible. In particular, we'd like to thank Tage Svans Stiftelse för undervisning och forskning, Beijerstiftelsen, and Kungliga Patriotiska Sällskapet. And of course, we'd finally like to thank all of you for listening. Thank you.
Thank you.
Thank you so much, Casper and Clara. Does anyone in the audience have any questions you'd like to ask?
Yes?
How are isomorphism checks made? Is like one graph compared to all other graphs, or how does the algorithm do it?
The algorithm we used, if we can go back to this slide, we essentially checked every single permutation of every single way to arrange these vertices, which there are, in this case, 4 factorial of, but it scales up very quickly. And then for every such permutation, we check if the edges are connected in exactly the same way.
Yeah, so that was the main isomorphism check. But we also had a fast one before doing the slow one to save some time. So the first one consisted of counting the amount of double edges and the triple edges, and then cycles of length 3. Yeah, before doing the so one to optimize.
This faster isomorphism check was able to dismiss approximately 90% of all isomorphisms for family graphs with 9 vertices, which saved a very large amount of time. Aman?
Yes, for all the Feynman graphs you generated, were you able to keep track of which vertices were external? Or, sorry, yeah, vertices.
Yeah, because external vertices have the defining property that while all other vertices of a Feynman graph has degree 4, external vertices only have degree 1. So they're easily identifiable.
Yeah, okay. Thank you, Casper and Clara, once again, for presenting your research. Okay, next up is Emily Liu. She studies at Göteborgs Högre Samskola and has also attended other summer programs like the International Summer School at Cambridge. We are now going to hear about her project on gene response to leukemia treatment. Welcome up, Emily.
My name is Emily Liu, and I've been working on a project investigating the effect of imatinib treatment on gene expression in K562 cells, which is the cell line from leukemia. And before I start my presentation, I would like to acknowledge my mentor, Sedat Akhtai, for his guidance and support throughout this project, and also my project partner, Amri. I would also like to extend my gratitude towards Race for Excellence and their partners, Tage Svans Stiftelse för undervisning och forskning, and KPS. So the cell functions in our body are controlled by genes, and they're regulated by gene expression. And sometimes mutation happen in the cells, which in this study, when studying the cells of chronic myeloid leukemia, happen in blood stem cells. So it creates a fusion gene, and that increases the cell growth and prevents healthy cells from differentiating. Imatinib is a form of targeted cancer therapy, and what it does is that it inhibits the enzyme activity and stops the uncontrolled cell growth. So the question that this study aimed to answer was how imatinib treatment changes the gene expression. Cells were then sequenced using RNA, single-cell RNA sequencing that allows us to study each individual cell and the genomic activity in each single cells. The data that was collected was then filtered to remove empty cells and low-quality cells that could affect the results. And what my project has been focusing on is the data analysis part. So when studying high-dimensional data sets with, in this case, thousands of cells and tens of thousands of genes, it gets really difficult to compare and analyze. So to facilitate this, we compress the high-dimensional data into fewer dimensions. The first dimension reduction system that we used is called Principal Component Analysis, or PCA. And what it does is that it creates new principal components that captures the biggest variance in the data set. And so PC1 here contains the most information about the data. And in this plot, each dot represents one cell. The red dots indicate that the cells are treated with imatinib, and the blue dots are for control cells. So the cells have grouped themselves, or they've separated themselves into two different groups according to PC1. And what we learn from this is that imatinib treatment changes the gene expression in leukemia cells. The second dimension reduction we used is called UMAP, and what it takes these principal components and compresses them even more into 2 dimensions. And from this plot, we can see even more clearly that the cells have separated themselves into 2 distinct clusters. The blue cluster represents the control cells, and the red clusters are the imatinib-treated ones. And note that the imatinib-treated ones are divided into 2 smaller clusters as well. One smaller cluster and then a larger one, which means that different cells respond differently to treatment. And then we used the same UMAP plot, but we clustered the cells into smaller subcultures, seen in the picture to the right. And by comparing these 2 plots, we can see that cluster 0 and 2, so the green and the red clusters, represent the control cells, while cluster 1, 3, 4, and 5 are the imatinib-treated ones. So from this result, we can compile all these information into one heat map. And I know that it might seem pretty intense in the beginning, but let's break it down. So on the top, we can see the different clusters created, with each row in this heat map representing one unique cell, gene, and each column representing one cell. And all the pixels are the gene expression level of a specific gene. So yellow color means high expression, while purple means low expression. And by looking at this heat map, we can see clear resemblances between cluster 0 and 2 in gene expression. So they express the same genes, basically. So for example, if we look at the genes in the middle, they control ribosome production and mitochondrial activity. So basically, metabolism and nutrition. In the cancer cells, these genes are highly expressed, so the cancer cells can produce a lot of energy and also proteins in order to reproduce really quickly. And then after treatment in clusters 1, 3, 4, and 5, the gene expression is lower, and we can see that by the purple color, and that indicates, or that means that the cells can't produce as many proteins and as much energy needed, and that controls the cancer and prevents the uncontrolled cell growth. And if we look at the 10 genes in the bottom that control cell reproduction and also programmed cell death, we see that clusters 0 and 2, so the control cells, have very low expression. So they don't, they've lost their ability to know when to perform programmed cell death when sick. While the clusters that were treated with imatinib show higher expression of these genes, and especially cluster 5, that is really yellow, so very high expression of the genes. So those cells in cluster 5 have regained the function to know when to perform programmed cell death, and also slows down the cell reproduction rate, so it slows down and eventually stops the growth of cancer. So what have we learned from this? First, that imatinib treatment affects and changes gene expression in leukemia cells, and that it lowers gene expression for metabolism and nutrition, but it increases the gene expression for genes that control functions like programmed cell death. And it's also important to remember that every cell responds differently to treatment, and that could be used in future studies to combine targeted cancer therapy methods, because they can target different subcultures in cancer to make the treatment more effective. And so from these results in this study gives us a deeper understanding of the CML cancer mechanism, and provides us with an insight to potential resistance mechanisms, which could, or pathways that could help us improve treatment methods for chronic myeloid leukemia in the future. Thank you for listening.
Thank you so much, Emily. Are there any questions from the audience? Seems like you understood it all, and now you know everything about leukemia treatment. Thank you so much, Emily. So, the next presentation will be about quantum algorithms, and will be presented by Simon Granström. Simon studies at P.A. Fogelströms Gymnasium, and his interest in physics and math led him to both extra courses and various competitions. Welcome up, Simon.
All right. What do bombs, multitasking, your private messages, and factoring all have in common? If your immediate response wasn't quantum mechanics, I'm here to convince you otherwise. My name is Simon Granström, and I'm here today to introduce you to the topic of quantum mechanics and quantum algorithms. We'll begin by going over some key concepts and topic of quantum mechanics, and then move on to see how we can apply these to create and understand quantum algorithms. We'll end by looking at a specific quantum algorithm, known as Shor's algorithm, which has had a pivotal role to play in the field of quantum mechanics and society as a whole. But first off, what is quantum mechanics? Could everyone here who's ever heard about quantum mechanics before, please raise their hands? Great. And now, could everyone who think they understand quantum mechanics, please raise their hands? I see we have a liar in the crowd. Because in a very real sense, no one understands quantum mechanics. Quantum mechanics is so far removed from our intuition and how we normally like to think about the world that it breaks everything we thought we knew about reality based on our daily life experiences. So, if you ever think that something's confusing or that something's hard to understand, just keep in mind, you're doing it right. But now, the two key concepts I want to go over in quantum mechanics are superpositions and interference. And I want to do this by painting you a scenario. Imagine you have a stockpile of bombs, and you want to figure out which of these bombs work or not. And furthermore, these bombs are constructed in a very particular way. And this is very important. Every bomb has a light sensor that when a particle of light reaches it, the bomb immediately explodes, if it works. If it's out of order, the light sensor works just as a transparent piece of glass, letting light pass through as if nothing ever happened. So, what's the best way we can test these bombs? Classically. And really, the only way to do this is by individually sending single particles of light at each sensor and detect what happens. If nothing happens, then great, the bomb's useless, throw it away. Though, if something does happen, we won't really have learned much in the end anyway, would we? We'll just have a crater in the ground. So the question then becomes, can we do any better? And it turns out that the answer is yes, by utilizing quantum mechanics. And the way we'll do this is by studying a thing called the Mach-Sender interferometer. And it works in a quite simple way. Imagine we have a laser which shoots single particles of light at a beam splitter. This beam splitter works in such a way that 50% of the time it just lets the light pass right through. The other half of the time it's reflected. Independent of the path the light takes, it's reflected by mirrors into a second beam splitter, which works in precisely the same way. Then, after this, there are two light sensors, 1 and 2, which detect the light coming out of the second beam splitter. So, what one intuitively would expect to happen is that we detect equally as much light in sensor 1 and sensor 2. This is not the case. In reality, sensor 2 detects no light at all, and detector 1 detects all the light. This is due to the fact that when the single particle of light reaches the first beam splitter, it's put in a superposition between going straight through and being reflected. And these two different positions states that the light can beam interact differently with a second beam splitter, and they cancel each other out in the direction of the second sensor. They destructively interfere, whilst in the direction of the first sensor, they reinforce each other, constructively interferes. Now, ponder what might happen if there's some sort of disturbance in our circuit, that one of the paths is somehow blocked. What now happens is that the second beam splitter works exactly as we might expect it to, and sensor 1 and sensor 2 detects equally as much light each. How is this useful? Well, imagine instead of some disturbance, we place our bombs in the circuit. If the bomb is out of order, the light sensor will just let the light through, putting us in the first scenario where we do that. We must infer that the bomb was in order, because if it wasn't, we would have never detected any light in the second sensor at all. Now, of course, there's also an immediate 50% chance of the bomb just exploding, but that's besides the point. Quantum mechanics has achieved something that would never have been possible without it. Okay, how can we apply what we learned about quantum mechanics to create quantum algorithms? And the basic thing about quantum algorithms and how they operate are they use qubits. Qubits work much like regular bits in a classical computer, in which they can exist in one of two states, 0 or 1. The main difference being that a qubit can exist in a superposition between both 0 and 1, acting kind of as both at the same time. And now, what makes most quantum algorithms special, what makes them more powerful than any old regular algorithm, is what's called quantum parallelism. Quantum parallelism basically compresses a bunch of computations into just a single one by utilizing the superpositions of our input to the function. Though this might sound extremely great, and in a sense it is, there's a catch. Because quantum parallelism preserves superpositions. So when we input a bunch of superpositions into some sort of function and get an output, our output remains in a superposition. And so when we measure it, we get no real useful information because we just get a random output. Basically what any old computer could have done anyways. So the hard part about creating a quantum algorithm is to make all the output values, which we do not care about, destructively interfere, whilst the output values, which we do care about, constructively interferes. And as a matter of fact, this is so hard that up until 30 years ago, every single quantum algorithm created only solved a problem which was created after the algorithm itself. Up until 1994, when Peter Shor created Shor's algorithm. What Shor's algorithm does is really quite simple. It factors numbers. Take the number 6 for example. The number 6 can be factored into the numbers 2 and 3. That is, 2 times 3 equals 6. So inputting the number 6 into Shor's algorithm would give you the numbers 2 and 3. Though the largest number, which is yet to be factored using Shor's algorithm, is 21. This is the circuit for factoring the number 21. Though this might not sound all too impressive, and it definitely isn't, like anyone could factor 22, 21 in their head, this might actually be a good thing. And the reason for that is the internet. With the internet, messages are sent left to right, north to west, east to south, all the time. And whenever a message is sent, any third party could just pick up a message and look at it. What hinders them from gaining any useful information from this is what's called encryption. Every message sent across the internet is encrypted, made into gibberish, which makes it impossible for any third party to actually read what the sender and the receiver wants to communicate with each other. The only problem is, the most common method for encryption today is RSA encryption. And it relies on the fact that it's supposed to be hard to factor numbers. So when Shor's algorithm comes in and says, hey, I can factor every number you could possibly imagine, the whole internet starts to sweat a bit. And what do? I mean, obviously there are other methods of encryption, but a lot of them have also been proven to be able to be decrypted by other quantum algorithms. And for the encryption methods, which haven't yet been cracked, there is no guarantee that they won't ever be. There is also a notion of quantum cryptography, which is in a sense impossible to decrypt. The only problem is, it's quantum. It can only be run on a quantum computer. So, if we still want to use classical computers after the fact that quantum computers have gotten good enough to factor large numbers, we're still in trouble. Though this might sound quite grim, there are also quite a lot of positive things with being able to factor numbers. And it relates to a concept in computer science, where we try to categorize different problems based on how hard they are to solve. In particular, there's a certain class of problems called NP problems. These are problems which are in general hard to solve, but easy to verify solutions to. Take for example factoring. It's quite easy to verify whether a number is a factor to another number, but it's quite hard to find the factors of a given number until Shor's algorithm came in. And we all realized the factoring was in fact not an NP problem, but a P problem, which are problems which are easy to solve and easy to verify. So the question then naturally becomes, can quantum computers solve any other NP problems? And in particular, can they solve a certain type of NP problem called an NP-complete problem? Because if it manages to solve an NP-complete problem, it can solve every single possibly imaginable NP problem. And as one might imagine, there are a lot of problems out there which are hard to solve but easy to verify the solutions to. For example, Klarin Kasper's graph isomorphism problem would be one of these problems. But then the question becomes, how realistic is all this? And experts predict that about 5,000, 10,000 qubits is what is necessary for a quantum computer to be able to do something productive, something which we couldn't have done otherwise. Still, though it might appear as though we're quite some ways away, I believe it's important that we sit down and have a discussion about the applications and ramifications of Shor's algorithm and quantum algorithms in general. Because the matter of fact is, we are running out of time. Thank you. I would also like to quickly just thank some of the sponsors for RAISE for making all this possible, and of course my fantastic mentor, Johannes Landsteiner, for all the amazing conversations about quantum mechanics and research in general. So, thanks.
Thank you so much, Simon. Are there any questions from the audience?
Yeah. So why is Shor's algorithm not able to factor numbers larger than 21?
Because constructing a quantum computer at this point turned out to be quite hard. Nature doesn't seem to approve of superpositions in general, at least on a global scale. And things tend to want to interact with other things, which basically makes the superposition collapse. And without any superpositions, we can't really utilize quantum computers or quantum algorithms at all.
Very interesting. Thank you so much, Simon. Okay, next up is Augusta Wiltermuth Rampe. She studies at Procivitas Helsingborg, and she is experienced in competing, both in biology and chemistry, as well as diving and gymnastics. She is now going to tell us more about her project and immunology. Welcome up, Augusta.
Thank you. And thank you, Simon. That was an amazing presentation. I hope you're all not too tired after thinking about quantum mechanics to hear me talk about the immune system for a while. There it is. I have been studying the immune system, and specifically cytokines that are a type of molecules used for communication between immune cells. I've been doing this at Karolinska Institutet under the direction of Alexandra Argiriou. Thank you so much for coming. And I've had a very good time. Anyway, specifically what I have looked at are these two cytokines, type 1 interferon and interleukin 8, or IL-8, and the cells that produce them. And I'm sure that most people in here have never heard about these cytokines, but they do a lot for you, and you should be very grateful that you have them. Type 1 interferon is produced when immune cells detect a virus, a viral infection. And when they reach their target cell, they make it much harder for the virus to replicate in that cell and to spread to other cells in the body. Type 1 interferon also activates other parts of the immune response and makes it easier for the immune system to combat the viruses, which is super important. Interleukin 8 also reacts when the immune cells detect a pathogen in the body, but it has a completely different function. It attracts, recruits immune cells from other parts of the body to that site of infection, to the place in your body where the pathogen has entered, maybe a cut in the skin, for example. And specifically, IL-8 recruits neutrophils, one of the most common immune cells. And of course, I've been talking about these cytokines as if they exist in isolation, act in isolation in the body, which is completely not the case. The immune system is very complicated and very interconnected. You can think of it as like a big knotted together piece of yarn, and you can pull on one of the threads in the yarn, and inevitably something else will start moving and be affected by that, and in turn affect that thread. And for the purposes of this presentation, I will simplify, I will cut out the thread that I'm interested in and just talk about that. But in reality, in real life, in vivo, in the body, things are much more complicated. So that's good to keep in mind. Anyway, I started out with 2 samples of cells from 2 healthy donors and their blood. I used 2 samples, did all the experiments twice, so that I could compare the results and be slightly more confident in my conclusions. Of course, more samples would have meant even stronger conclusions, but you know, time constraints. And what I wanted to end up with was this. I wanted to study how plasmacytoid dendritic cells, or PDCs, produce type 1 interferon and interleukin 8 when they detect an infection. But I didn't just have this. I had a bunch of immune cells. So you have to somehow find a way to get from a lot of immune cells that do a lot of different things to be able to just isolate and look at this specifically. The way we did this can be described a little bit like this. We started out with the frozen cells. Then we took very good care of them, made sure they had their nutrients and were happy. And then we made them not as happy by stimulating them, making them believe that there was an infection. The way we did this was by adding something called a unmethylated CpG oligonucleotide, which is a mouthful. Basically, it mimics microbial DNA. So it makes the immune cell think that it has detected microbial DNA, which is not supposed to be in the body, and probably means that there's a pathogen in the body that's not supposed to be there. And this initiates an immune response. The way in which it does that can be described by this image. The CpG stimulant enters the cell, where it binds to a receptor called TLR9. This receptor sends out a signal that starts gene regulation. And basically, the genes for type 1 interferon and interleukin 8 are turned on. The cell starts to change its behavior, and it starts to produce these molecules. After the stimulation, or after we added the stimulant, we had to find a way to actually be able to detect these molecules produced. And we had to find a way to distinguish the PDCs, the cells we were interested in, because, of course, we had the sample with a bunch of different immune cells, and we were not interested in, for example, what the T cells were doing. The way in which you do this is called antibody staining. An antibody is really good at binding to a specific structure with a specific shape. And you can design antibodies to bind to whatever you want. And there are a bunch of different options of things you could design them to bind to. There are proteins on the surface of specific cells that, only exist on the T cells, for example, or the B cells. And I had added antibodies for all of these, so that I then could exclude them when I was analyzing the data. You also need antibodies that bind to the molecules that you're interested in, the cytokines, type 1 interferon and IL-8. But to do this, to stain for those molecules, you have to get the antibody inside of the cell. So you kind of punch a hole in the cell membrane, get the antibody inside the cell, and then you shut off the cell membrane so that the cytokines aren't secreted as they normally are, because we want them to stay in the cell so that we can analyze them and the levels. After the stimulation was added and the antibodies were added, the cells were incubated. Basically, they were put in conditions that are similar to what exists in the body. We had 3 groups. One was incubated for 2 hours, the other for 3 hours, and the last for 4 hours. and then we studied what had happened in the cell after all of these incubations. The analyzation was performed using a technique called flow cytometry. And this is where my project suddenly became physics, which I wasn't really, I wasn't really expecting that, but it was very interesting. Flow cytometry works, it utilizes light. So you shine light on the cells, and depending on which antibodies bound to what in those cells, and depending on other characteristics such as the size and the complexity of the cell, the light will be scattered in different ways. And depending on how the light is scattered, what wavelengths of the light detected are most common, you can then draw conclusions about how the cell looked, what type of cell it was. So these were our results, or some of our results. And we were very happy when we saw them because they indicate that the stimulation was successful, which is very good because then we can actually look at what happens if the PDCs think there is an infection. The way in which we know, or one of the ways in which we know that the stimulation was successful is by looking at these two plots. They show all the cells, all the data points, and their size and their complexity. And what we can see is that the stimulated cells have increased in size more than the unstimulated control has, which indicates that there was a stimulation. Another thing that we can see that was very nice is that after 4 hours of stimulation, 4 hours of incubation, the stimulated cells produce some cytokines. Specifically, they produce interferon alpha, which is one of the type 1 interferons, and IL-8. For interferon beta, we didn't see as much of a production, which most likely just means that the cells need more time before they start producing them, which is also very interesting to know, and the reasons for that are very interesting to study and learn more about. And this is also only after 4 hours of stimulation. After 2 hours and 3 hours, we saw almost no production. So something happens there in between. And this initial response is also very important to study because different people have different initial immune responses. And depending on how quickly your immune system reacts and how strongly, the course of the infection or the disease might be very different. You might have a quick initial response that then is over after not so long of a time, and that might lead to a mild case. For example, this is the case with COVID-19. If you have a quick interferon production and then it's not too prolonged, that might lead to a milder case. But if the interferon response is delayed and then prolonged, that could lead to a much severer case of the disease. And these differences between different people were completely expected because of genetic differences. One other reason why one of the samples produced so much more cytokines so much quicker might be such a simple thing that that donor had an infection when they gave the sample. And that infection that hypothetical infection might have led to gene regulation so that the PDCs already produced cytokines, those genes were already turned on to produce the cytokines, which would have led to the production being quicker when we stimulated them. For example, though I only studied these cells and the stimulation in quite short incubation times, quite short stimulation times. It would have been very interesting if I had had the opportunity to follow these levels of the cytokines for a longer period of time. Normally, when you do these stimulations, you do them for maybe 7, 9, or even 20 hours. And then you can tell more about the full response. I can only draw conclusions about, for my samples, the initial responses. So I wish I would have had the time to do even that as well, but I'm very happy that I got to do what I got to do, and I'm very grateful for everyone who made that happen. First and foremost, thank you so much, Alexandra. You've been amazing, and also thank you to the entire team at the rheumatology division. They were so nice, and they really took me in and took care of me. It was very nice. I also want to thank Race for Excellence and their partners who made this possible through their donations. Thank you, Stiftelsen Oskar och Maria Ekmans donationsfond and Vejo Stiftelsen so much. And of course, I want to thank the Race community, this year's organizers, all the other students here who've made this experience so wonderful, and of course the previous students from other years who came and helped us and proofread my report. Thank you so much, Philip, for all that help, and thank you everyone for being amazing and making this possible. And thank you for listening, of course.
Right. Thank you so much, Augusta. Are there any questions from the audience?
What wavelengths of light are used so that they don't damage the cells that they're being shined upon?
Very interesting question. I don't know the numbers, but I know that the type of flow cytometry we used has detectors for, I think it is the entire visible spectrum. Is that correct, Alexander? Yes, yes. So the wavelengths are different parts of the visible spectrum. And you'll have one antibody that sends out a signal in one part of the spectrum, hopefully very small and very specific, and you'll have another antibody at the other part of the spectrum. Because if they overlap too much, it's really hard to tell which signal comes from which antibody. Yes? That is called permeabilization buffer, a permeabilization buffer. We call it a perm buffer for short. Basically, it does, yeah, it creates hole in the cell membranes. Yeah, and then the other buffer used to stop the secretion is called BFA, and what it does is basically block vesicle formation so that the cells can't produce the kind of small bubbles they normally use before they send things out of the cell. Yes?
How did the results of the interferon production differ between the different incubation?
Yes, good question. They were type 1 interferon. Type 1 interferon beta was pretty much not expressed at all, even though we had 4 hours of incubation time in the stimulated cells. And the other two, or interferon alpha, was produced after 4 hours of incubation. Maybe you could see some signs at 3 hours, and at 2 hours you could not see any signs of interferon alpha. Anything else?
No?
Thank
Great.
you so much.
Thank you. Alright, next up is Oskar Berg. Oskar, a champion weightlifter and physics enthusiast, studies at Campus Victor Rydberg here in Stockholm. He is now going to present his project on comparisons between photoelectric effect and gravitational waves. Welcome up, Oskar.
All right. Okay. As a wave, which it is true. It sort of behaves like a wave. It can be described as a wave. It is correct. But then a huge discovery was made. Then not only made a question if light can truly be described as a wave, but also if we can describe the world as we know it with with classical physics, and that would be the photoelectric effect. And what the photoelectric effect showed was that, let's say you had this wave of light, and if it would strike a metal surface, then if it was of a certain frequency, then it would eject an electron, but only if it was of a certain frequency, which didn't really make sense, considering if it truly was a wave, then why wouldn't we be seeing sort of a linear absorption of energy? Well, this was kind of mind-boggling at the time, because we didn't really know why. It was only dependent on the frequency. And even if the frequency of the light was above this threshold, you wouldn't even see this linear absorption of energy. Instead, what you would see is a discrete absorption of energy. And this is kind of strange also, because this is sort of a particle, this is sort of familiar to what particles do. So what Einstein proposed was that these energy bumps, these discrete energy levels, would each represent sort of a light particle that would carry energy. And those particles would be called photons. And thus the concept of the wave-particle duality was introduced, and waves, or rather light, could be described as both a wave and as a particle. Now, if we move on to gravity, or rather, let's take a look at light for a second. Light has a field, electromagnetic field, and light has also a wave, electromagnetic wave. And now it also has a particle called photon. If we look at gravity, gravity is a force. Gravity also has a field called the gravitational field. And it also has gravitational waves, as we sort of recently discovered. Right. So why shouldn't there be sort of a gravity particle? Well, it turns out that there actually is. Or that it could perhaps exist, theoretically. Anyway, it would be called the graviton. It's not detected yet, but it theoretically exists, let's say. So, in order to detect this, why can't we use sort of a gravitational version of the photoelectric effect? Well, a complete replication of the photoelectric effect using gravity won't really work. This is because a gravitational wave is simply too large. It cannot eject a single electron. So what we can use instead is essentially sound. And we can use the particle of sound called phonons. This would mean that we would have a gravitophonic analog of the photoelectric effect. And the way this would work, let's say we have two black holes emerging, epically colliding. Anyway, then they would emit gravitational waves, just like this. And then, let's say we had a detector of sound. This detector of sound would then sort of absorb single gravitons. And the way that it would detect it would be that we would see an increase in the energy of the detector. The phonons, or the particles of sound, would begin to oscillate. They would essentially begin to move around. And we would see this energy jump sort of be discrete instead of sort of a buildup, right? And this would essentially be what a graviton is. So an energy bump, just like a photon, right? And it should be noted, before going further into the photoelectric effect, that since the gravitational field and the electromagnetic field can both be described using similar wave functions, they can sort of be used interchangeably, which means that almost every finding that we can discover when we dig deeper into the photoelectric effects can be applicable to the sort of gravitational analog of it. So, there are three core signatures of the photoelectric effect. Now, the first one is obviously a frequency threshold. There is a certain frequency that the light has to have before the electron can be ejected. This means that it can't be a sort of a build-up, sort of a delay either. It has to be above that threshold, no matter the intensity of the light, whatever. It's only dependent on the frequency. And this means that the energy of the photon, the light particle, is proportional to the frequency of the light. And there's, of course, an instantaneous release of electrons. This can be sort of visualized with the instantaneous jump in energy. There would be sort of a sign of the photon, or the graviton. Now, what we did, me and my mentor, who is unfortunately not here today, what we did was that we reinvestigated this classically, using classical physics, to see where the classical physics would begin to break down, and where we would need to start using quantum theory. Because remember, if we can describe the photoelectric effect using classical physics, then this means that photons wouldn't really exist. And quantum theory wouldn't really be necessary. It sort of wouldn't exist in this part of physics either. So this means that we really need to dig down at where and pinpoint sort of where it breaks down and sort of what are the arguments against the photon and what arguments are for the photon, because then we can dissect them and apply them to the graviton. Let's move forward. So what we saw when we sort of reinvestigated it classically was that there was a smooth transition instead of an abrupt threshold of frequency. And what we also saw was the energy of the photon would be proportional to the amplitude or the intensity of the light, which then again, experimentally, is not true. This is not what they saw in the experiment. And we also discovered that it would technically be a build-up, right? It would not be instantaneous, since it's in classical physics is merely a wave. Now, we also modeled sort of energy between oscillators. And these oscillators would be representing a gravitational wave as well as a detector of sound instead of electrons, meaning that the increase in energy of the detector would hopefully mean a loss of energy for the gravitational wave. And this is exactly what we saw in these beautiful graphs. So, right here, we can see the blue graph is the gravitational wave, and the orange graph is for the detector in this case. So once they begin to interact, we can initially see that they both have the same intensity, they both have the same frequency, and they have the same energy. And just a reminder, this is all using classical physics. Now, once they begin to interact, moving along, after about 50 seconds, we can clearly see that the energy of the gravitational wave is significantly lower than initially. And simultaneously, the energy of the detector has increased equally as much as the loss of energy in the gravitational wave. Now, if we take a look at what happened with the oscillators, we can clearly see that the amplitude or the intensity of the gravitational wave has been lowered, and the amplitude or the intensity of the detector, the phonons or whatever, have increased. So this is sort of evidence for our classical analysis. Now, if we move on to sort of semi-classical physics and sort of a quantum analysis. So the way we did this was that we quantized the energy levels for the detector oscillator, meaning that we sort of, instead of having this linear energy, we would instead be seeing sort of bumps, discrete bumps, just like we saw experimentally in the photoelectric effect. Now, what we got was essentially probability for the detector to jump up to that energy level that would be proportional to the energy of either the photon or the graviton. Just like this, right? We would see the probability for it to jump up here. And this energy difference would be the equivalence, the energy of a graviton or photon. Now, what we also discovered was that when looking at the ensemble average. Now, what ensemble average is basically if we have a whole lot of these quantum states, that is essentially the ensemble, right? A whole lot of them. And if we take a look at the average energy levels, what we see is that classical physics can sort of predict these with an accuracy that is pretty well. So we essentially discovered that if we would have a whole lot of photons, let's say a wave, then classical physics would be able to predict sort of the average energy of that entire wave. And this really highlights the transition from quantum physics to classical physics, where you would need quantum theory to sort of describe single particle transitions. And looking at sort of a whole lot of these systems, you would need to use, or you could use, classical physics. So the probability for the classical physics to be correct is pretty significant. Moving forward, we also saw that semi-classical physics also predicts correct energy levels looking at single particles. Now this could be quite concerning, since if classical physics can describe single particle transitions, this means that the photon would not exist and the graviton would not exist. However, this is if the law of energy conservation is violated, which it shouldn't be. What we saw recently with the graph was that the energy in the system was the same the entire time. Thus, it should not be violated, right? So, since energy should be conserved, this means that we must essentially discretize the field of both the gravitational and its sort of light counterparts, which would require quantum theory, just like this. Right, and this is all, of course, applicable to the gravitational wave. So, to conclude, since energy conservation at single particle transitions should be conserved and should be applied to the photoelectric effect, this means that discrete quanta of light, or as Einstein called them, photons, are required. And since discretization, or sort of quantization, of the field applies to both the electromagnetic field and gravitational fields, there should probably be gravitons. Theoretically, they should exist, right? And we probably need further experimental studies to determine how analogous the photoelectric effect and its gravitational counterpart really are. But yeah, the graviton should probably exist. So yeah. And lastly, I just want to thank RACE for excellence and their partners, Stiftelsen Lars Hiards Minne and Beijer Stiftelsen, for making this possible, and everyone else at RACE and the community and everyone here listening today. So yeah.
Thank you so much, Oscar. Are there any questions from the audience?
Okay, this may be a little bit of a simple question, but we can know how particles usually interact with fields, say an electron with magnetic field. We know how photons can be affected by gravity, say an example is black holes. But then how would two particles, a photon and a graviton, how would they react with each other?
I'm actually not super. I haven't studied this question, but I know that we probably have one in the back called Alan, who probably studied it. But yeah, there is something about what's called the inverse Gertenstein effect. But yeah, yeah, I can't really answer the question. Yeah, but it's an interesting one.
I'll answer the question later for you.
Yeah, no spoilers, right?
I kind of agree with some questions, but like to begin with, what is a photon?
Well, it is. You can view it as like a vibrational particle of sound.
Like just any student particle?
Yeah, it's sort of yeah, like a quantized.
And why would like gravitational waves interact with?
Well, you would consider sort of massive quantum systems at very large scales, and then the only thing that sort of we would only have sort of sound that would sort of correspond to that, or sort of, we would need sound for it, for these massive quantum systems. That is what, as I understand it.
So then the question arises, why haven't we created a graphene?
So this method, well, it has really been used, but it's probably really hard to come up with, since you would need such large systems, and it's probably quite hard to detect gravitational waves to begin with. Yeah?
How does a phone work without any matter around? Because you say it's a summary.
Without any matter sort of in vacuum? Well, I actually haven't looked into it, but I mean, if it would be massless, then it would obviously be moving at speed, but yeah, I'm actually not sure. I haven't looked into it that much. It's my mentor's sort of project, seeing how that would work. I'm just looking behind the theory behind it. So yeah, but that is interesting.
Okay, thank you very much, Oscar. The last presentation before our lunch break is about how the brain perceives pain. It's going to be presented by Selma Lauer and Snezhana Polishuk. And Selma studies at Precivitas Malmö. She is passionate about both medicine and dance. Snezana, coincidentally, is also a dancer and studies at Kunskapsgymnasiet in Norrköping. And she has also previously conducted research about breast cancer. Welcome, Selma and Snezana.
Everyone hears me, right? Okay, sounds good. Please raise your hand if you know someone who suffers from chronic pain. Like maybe a person who almost every single day tells about their pain in their back or their joints, for example. Yeah, quite a few. Today, statistics tells us that about 1.5 billion people in the world experience this every single day. And most treatments today that exist for this issue are highly invasive or have a lot of side effects, which actually doesn't always depend on the limitation of precise technology. We're quite advanced in that matter at this point, but rather on the lacking understanding of anatomy, especially the brain's anatomy where chronic pain is perceived. And it's logical, because let's say you have an enemy hiding in a dense forest. The only way for you to reach him if you do not know his location is to probably kind of fly from a bough and spot him and then throw a bomb. Or set the whole forest on fire, hoping that it will reach him as well. And while you may reach your goal of defeating the enemy with this tactique, you also end up damaging all the surrounding areas and creating a mess of the forest. However, if you now instead have a map that shows precisely where your enemy is, you can confront him directly and face him face to face. And who knows, you might even reach a compromise without having to destroy the entire forest. And this is what our research focused on, tracing and mapping the regions involved in pain perception, aiming to provide more precise and better ways of targeting pain. Because in medical terms, we could say that the enemy are the regions of the brain that receive and project the sensations of pain. And the map symbolizes our precise understanding of the pathways involved. This analogy was meant to show that while advancing our bombs or diplomatic skills is crucial, it's equally important to take time to actually understand the pathways behind pain. This understanding can then lead to more targeted and less invasive solutions.
Well, the anatomy is important, but how does pain actually work? What is the anatomy behind it? Pain can be caused by different stimuli. It can be thermal, chemical, or mechanical, if I hypothetically punch Snezana. Then her pain-sensitive receptors will react, and they will send sensory information and signals to the spinal cortex, and this is the pain transmission. Furthermore, the signals will continue to the brain, specifically to the thalamus, which will send these signals to different brain regions. The thalamus is very important. It is located above the midbrain, and it works as a relay station that sorts these sensory signals and sends them to different parts of the brain. A specific part of the thalamus is the ventral medial nucleus of the thalamus, or simply put, the VM. The VM is shown to be related to pain, which also, because it's part of the thalamus, is like a relay station that sorts these signals and sends them to different parts of the brain, specifically the cerebral cortex. And studies have also shown that it sends particularly to motor areas that are related to movement, which is very interesting. We have this protein, calbindin-1. It is a calcium-binding protein that can regulate the calcium levels, and therefore it is used as a marker
in different methods related to, for example, our experiment. When the calcium levels are regulated, it can either excite or inhibit these neurons in the brain, and therefore it is some way related to pain, which is still a bit unclear. And this image shows the different dots and where calbindin 1 is expressed in the brain as the dark purple dots.
So now, in order for us to be able to map out the regions involved in pain, we needed brains and colors. However, we didn't do this manually. We didn't breed our own mice and dissect their brains, thank God. I'm really glad. But instead, we used this amazing open database provided by Allen Institute. All the experiments they conduct, they put online, so anyone, yes, even you, can access it. However, without prior expertise in neurobiology, it might feel a bit overwhelming. But let me try to explain how we found the specific experiments that could answer our question. All the dots presented here are experiments, specifically injections with a tracer or a collar into the respective brain regions. And we, to find our answer to our question, we filtered out our mice type, specifically the transgenic calbindin 1 Cree mice, and chose our color, tracer EHFP. In simple terms, this just means that when we will click on the experiment, all the neurons that contain the calbindin that Selma talked about, they will fluoresce, like in the image here. Okay, wait, maybe still too much information. Transgenic calbindin, well, the only thing you actually have to understand here is the calbindin calbindin protein. The reason for why we chose specifically this protein as our marker for pain pathways is quite simple. It was previously shown to be involved in pain perception. In detail, one study showed that mice who didn't have this protein, had an increase in pain threshold, suggesting that you, at least to some extent, need this protein in order to feel pain. And now, when we had filtered everything out, we were left with these data points. Feels so much better, right, to look at. And you see this big dot in the middle? That's the experiment we chose. Now, based on the theory that Selma presented to you, can you guess what part of the brain it is? Let's play Dora the Explorer. I'll count down and we'll shout it out together, okay? So 3, 2, 1, thalamus. Nice, you're so smart, guys. I'm very proud. Yes, and now we finally had our experiment. And the real work began. Yes, what we basically did is what this Selma is demonstrating right now. We had the atlas on the left, and we had the images on the right. Then we looked at around 140 images, probably even more because we were looking through the same images multiple times, going from anterior toward the posterior. And we were noting down all the areas that we saw being fluorescent. And yes, I know that many of you have this question. We did feel unnecessary because AI could have probably done this so much better by just overlapping the images and giving us the data. However, this type of work is actually called blind analysis and is usually done prior to looking at quantitative data to ensure more reliable results. Because after hours of tedious work, we got to know that there actually were numbers all from the beginning. But let's first look at what we observed with our visual assessment.
So the first thing we observed was that the VM, which I recently spoke about, was labeled. And this was not unexpected because the VM was, after all, the injection site. So it was colorful and fluorescent, as you can see on the image. And the fibers continued to travel along the brain to the CP, and then to the MOP and MOS, which are the motor areas, the areas involved in movement. The MOP and the MOS are shortened for the primary and the secondary motor cortex. It is primarily seen in layer 1 and layer 5 as the most labeled, and therefore we can say that the motor cortex was the most labeled according to our visual assessment. There were other interesting results. We found that the so-called orbital areas, which are shown to be related to cognitive functions such as decision-making, that they were labeled as well, which is interesting. And still, the motor areas were the most fluorescent according to our observations.
And now for the numbers, or almost. Here, besides coronal sections, the database also had information about the volume of labeled fibers in different regions. Okay, sorry, again, too many technical terms. Labeled is basically the same as projecting or fluorescent, and fibers is, you could see it as a synonym to neurons. And this data we compiled in this beautiful chart. All these circles represent a region in the brain, and the size of the circle just tells us the volume of fluorescent neurons in that specific area. And the higher the volume is, the more neurons that are involved in this pathway, the more important they are considered in pain perception. And here we can quite easily see that MOS, CP, and MOP were the strongest ones, had the highest involvement. However, you might also probably notice that the bubbles have different colors, and it's not a coincidence. The colored bubbles are the ones that we observe by our visual assessment, while the gray ones are the ones that values tell us are important. However, we didn't find them significant when we're looking at the images. And if you look a bit even more closer, you might notice that many of these bubbles have an SS in them, standing for the somatosensory area, the part of the brain that discerns sensory information. But how come we had this discrepancy? Let's investigate together. This is what we saw when we were looking at the somatosensory region. Doesn't really seem very fluorescent, right? That's what we also thought. However, when we looked back at the data, came back to the images, we noticed that although the somatosensory region wasn't shining brightly, it was present throughout many sections. In fact, these sections are 12 images apart from each other, starting from when we first time see some labeling in the somatosensory area to when about 36 or 24 images later when it's not labeled at all anymore. And do you see where I'm going? So the somatosensory area might not have been strongly labeled or shining fluorescently on individual images, but since it was present throughout many images, it was spread out and got similar values to orbital layers that were shining really strongly, but only for a short period of time. And it becomes even more evident when we look at it from sagittal view.
Another very interesting bar graph we created was this one. And we can see that it shows the different volumes of the different brain regions and their layers. We can see here that the motor areas, MOS and MOP, were the most fluorescent and labeled, especially layer 5, which is shown as the green color here on the graph. A close second is layer 1, which was also very fluorescent. But according to our observations, we saw that layer 1 was the most fluorescent in our visual assessment. But we can see here that it is layer 5 that is the highest on the graph. Well, why is that? Well, it can be explained with the same explanation as Snejana just said. Because layer 5 has a bigger area, but layer 1 is thinner. So it may seem to be more labeled in one image. However, if we see over like a bigger volume of the brain, it is layer 5 that is most prevalent and present. And therefore, this can be explained why layer 5 is the most apparent in the brain regions.
So now, our results indicate that the motor regions were the strongest in pain perception. So the regions in the brain that control our movement and decision-making about our movement are the most critical ones in pain sensations. Wait, like pain is a feeling, right? Like I feel that it hurts when she punched me previously. I feel. And it's a sensation. And we did actually show that the somatosensory region, you remember the gray bubbles with SS, were involved. However, our data quite greatly, both visual assessment and quantitative, shows that the motor regions were more prevalent. And it's an easy explanation if you feel acute pain, because if you place your hand in a straw, you probably want to activate your motor regions to take the hand away. However, when it comes to chronic pain, after some literature review, we found that there were a few other studies that also pointed out the importance of the motor regions in pain perception, which means that we should definitely place more focus on understanding the role of the motor cortex in pain perception. Because focusing on these somatosensory regions that are already known and kind of intuitively predicted to be involved may be the reason for why many treatments are ineffective. We're simply not targeting the main issue of the pain.
Another very interesting result that didn't really have to do much with our experiment was the role of calbindin 1. Calbindin 1, as I explained, was a calcium-binding protein, and it can either make the neurons more excited or more inhibitory. But in this case, thalamus was excitatory because it relays signals. But the neurons and the pathways in our experiment were GABAergic, meaning inhibitory neurons. So the role of calbindin 1 is still unclear. Is it inhibitory or excitatory? And therefore, it is important to further investigate the role of calbindin 1. And with that, we can see what kind of treatments we can create. If, for example, the role of calbindin 1 is to excite, we can use treatment to inhibit so that we don't feel pain or chronic pain. Calbindin 1 may be a solution. And also focus on motor areas for treatments, because it is not sensation that, as Snejana explained, it may be the motor areas that are the solution.
So, yes. Now, please raise your hand if you know someone who has been treated from chronic pain. Well, a lot more few people who answered than previously. But we hope that our study and further studies can fix this, so many more people can live a life without having to suffer from pain every single day.
We want to, of course, thank our mentor, Roxana Khalid, for her expertise and for the experience. We want to thank the X-Rays for the feedback, and of course, Race for Excellence for this experience. And of course, their partners, Bayer Stiftelsen, AstraZeneca, Swedish Academy of Engineering Sciences in Finland, Tage Swan Foundation for teaching and research,
and you, our listeners.
Of course. Thank you for listening.
Thank you so much, Snejana and Selma. Are there any questions from the audience? Well, seems like you understand everything about pain perception now. Well, that was the last presentation before the break. We will be back with new presentations at 12:45, so please return in time for that. And have a nice break, and we will see you soon. Thank you.
Vi vet inte hur många som stänger av den.
Good. Okay, but exciting. Did you find a place for yourself or your friends?
I've got my own room. I think it's a shared kitchen. I haven't had time to actually do it. I paid for the flat.
Already?
I haven't been home.
But it's an exciting time, and I'm sure you'll enjoy it. It's a good time, I think. I remember these days probably. You get to know so many people, so many interesting people. So I mean, my contract runs out at the end of October. I'm doing and actually I will go back to Austria and find a job there. And I will continue with academia. It's a consultancy job in technology. Yeah, I thought a lot about it, but at some point I decided, well, I've seen enough of academia. It was fun and all, but thing is we don't need to we can just keep rolling and I mean, so many things will change. I think that's important. Don't try to make decisions 4 or 5 years in the future.
I'm sure you do.
I don't know. I mean, I think either way, whatever feels good is I don't regret doing my PhD at all. But I think also not doing a PhD will always have an interesting life.
Write to you because I want to try to have someone to keep in contact
Who knows how long I will wait?
I don't know the last
Maybe
names.
I'll
Find them on LinkedIn or whatever so I can keep track of them. Yes. Yeah.
Well, it was fun. Come again? Yeah, but I think so many people need to ask him questions and so on.
I wanted to ask him if
He did a good presentation, didn't he? It was very broad and yeah, we can talk about this one. We can talk about no, I mean, you remember me. I mean, I'm just sitting there and sometimes things come to my head and I'm like, oh, why don't we talk about it? Yeah, it was also a bit... but it was a bit unfortunate this year because I was also a bit sick and I had my family visiting for a few days. So I couldn't mentor some as much as I wanted to, but obviously it's managed somehow. Okay. So, but the stage is today and then you're going back to Palma. Military? Okay, shoot a gun.
No.
Brings the Korean military. There's new use for military in Sweden, isn't it?
Yeah, I mean... So, this was when we...
Wow.
And then I painted my face.
Wow. You like plants, right? And, I'm just asking the principal chat if it's safe for lunch or not. I'll talk to you later.
Hello. Nice to meet you.
well.
Yeah, very well.
Nu kommer jag försvinna lite. Eller jag har haft redan uppföljning uppdrag. Nej, men alla vet ju det. Vi ska hämta dvarvagnen i Säska.
That's good for me. Wait. That was definitely some of the best part. Reading through the papers. Okay. Well, it was really nice to meet you again.
Yeah. Okay.
And will you stay for later? Or
I don't think so.
all right. That's great.
Hey, have a great time. Let's stay in touch. Let me know if
we most definitely do.
Take care.
Well, goodbye. Well, also you let me know if you've accepted. I'll write your name on my resume.
Nej, vänta, vad alla gått?
distinkt. Det är inte alltså det som är gulligt med tanke på att alla har sin värld.
Jag tror inte vi kan låsa dem.
Nej. Men vi stänger den här i alla fall.
Ja.
Just jättesnabbt. Ja. den här. Men jag tror, alltså jag kan inte riktigt de där livsgruppsmål.
Vad är det då?
Hi, I'm Julina, and this is.
I am Benjamin.
And we have conducted a project under the supervisors, Professor Tom Britton and Dr. David Chan, titled The Role of the Lecture Period in Stochastic Economic Models, which is quite a mouthful, but that's also why we're here.
So, just a quick table of contents. We'll begin by introducing the topic of epidemiology, and specifically mathematical methods in epidemiology. We'll kind of explain why we are mathematicians and not biologists working on the topic of epidemics. Then we'll cover some of the most common and widely used epidemic models and some kind of categories here. The SIR models. We'll follow this up by introducing very briefly some of the most standard models used in the field, and namely the standard stochastic epidemic models is what we call them. We follow up this by introducing the mixing group model, which is a kind of novel extension or generalization published 2 years ago, which extends some of these break some of these assumptions of the normal epidemic models. Finally, we very briefly discussed the role of the infectious period, which is simply when an individual has contracted some pathogen, how long do they remain infectious for, and how does that vary between individuals? So, epidemics and pandemics are likely something we've all heard quite a bit about recently. But it is worth mentioning there is quite an important distinction. An epidemic is an outbreak of some disease, which is to some degree or to some extent contained, be that in a community, in a city, or in a country, but it's not everywhere. Pandemics can, being the Greek word for everything, are kind of omnipresent. So the recent coronavirus outbreak would have been a pandemic because it had a worldwide reach, whereas the Ebola outbreaks of 2013 to 2016 would have been epidemics. So the reason we're using these models, we're thinking about models for epidemics, is because they're not just biological phenomena, but also sociological phenomena. And by thinking of biological, sociological phenomena. So, to give an example, we have the disease Ebola, which was discovered in, I believe it was the Congo, in 1976. There was a second outbreak in 1979. But afterwards, there was a period of 14 years during which there were no outbreaks whatsoever. There were 0 recorded cases. But then there started being smaller sporadic outbreaks occurring occasionally, culminating in a very large outbreak in 2013 to 2016, where 30,000 people were infected, nearly 10 times as many as the second largest outbreak. So what we're thinking about with these ones is why can this happen? Why can there be some disease which is discovered, seemingly disappears for a very long time, then has small outbreaks, and then suddenly small sporadic outbreaks, and then suddenly a very large outbreak. So that's what we're thinking about when it comes to these models. And then also, you might be wondering, we're talking about epidemics, but we are not biologists in some sense. We're working with mathematics. So why can we use mathematics in the modeling of these epidemics? Well, it's because when we kind of consider people in aggregate, when we have multiple people together in some sort of grouping, these people behave in quite a predictable way. It might be hard to say how an individual would behave during a given time span, but a group of individuals, such as a workplace coming in and out, even though individuals may become late or have something else to do, we know that there will be some sort of regularity in which these people congregate and meet with each other. So what we're trying to do here is turn assumptions about behavior and behavior of people and spread of disease into forecasts and about how these outbreaks will unfold. So when we do that is we take certain key parameters about the disease we're trying to model, such as the basic reproduction roughly speaking, is the number of infections caused by a sick person. So, and then we're also thinking about further parameters, we don't list them all here now, but such as the transmission probability. And say, Julina here is sick, and I come into contact with her, what is the likelihood, how likely is it that I contract the disease from her? And then what we try to do with this is we try to estimate the probability of outbreak. We try to predict the size of them when they do occur. And then we can also look at more specific details, such as the peak number of concurrent cases. So how many people are sick when the most people are sick at the same time.
So it's impossible to create a model that encompasses all of the complexities of an epidemic outbreak. And that's why we make assumptions about how individuals in society interact and so forth. One such assumption is the SIR model. In the SIR model, the population is split into 3 compartments or groups: susceptible, infectious, or recovered with immunity. This model assumes a closed community. That is, there's no instances of births or deaths or migration in the community. So there are only 2 possible transitions. Susceptible individuals can interact with infectious individuals. For example, for example, if I'm susceptible and Benjamin here is infectious, and we can get in close or come in contact, and then there's some probability that disease will be transmitted, and I will in turn become infectious and start to infect others in the population. And after some time, I will recover. There are also other models, such as the SIR model, susceptible, exposed, infectious, and recovered. So there's some latent period before the susceptible individual is exposed and then becomes infectious. Then there are also diseases such as flu, which have no immunity, and that can be modeled with the SIS model. So you're susceptible and then infectious and then susceptible. And one of the most common type of epidemic models are standard stochastic epidemic models. These models are stochastic, which means that there's some stochasticity or randomness induced in these models in order to sort of emulate reality and how in the real world randomness has
We induce randomness to reflect some of the underlying uncertainties.
has some intrinsic
These models contain some degree of subjectivity, which means that
this is especially applicable in the initial stage of epidemic, where there's some, you have new infectious individuals, and there's some random chance that you never had interactions with other individuals during their infectious period, and thus a major outbreak will never
these models have the following assumptions. Just because the transmission is pairwise between pairs of individuals. So infectious individuals have some likelihood of infecting susceptible individuals upon contact. It's also true that we have a homogeneous community such that there's no distinguishable differences between individuals in society. During Corona, for example, we talked about certain risk groups who were more susceptible or vulnerable to transmission. But that is not the case in this model. And moreover, homogeneous mixing is assumed. So people have contact with every other individual in the population.
So one of the things we can think about is what happens if we assume that transmission occurs in groups rather than pairwise. This is kind of what's been thought of by the mathematicians Frank Ball and Juli in their 2022 paper. An epidemic model is shortly mixing groups, which, unlike the standard models, assumes that we have some randomly selected individuals in groups, random size, and transmission that only occurs within these groups. The rate and the size of these mixing groups are parameters which we can vary. So we can break the standard assumption of pairwise transmission and consider more groups as a whole and how these groups will affect it. So, to give an example, here we have an example of an epidemic with 10 individuals labeled 1 through 10 and mixing events labeled A through G. So you see here in the first event, we have individuals 3, 5, and 8 in A. Right? There are no infectious individuals. You see that because there's no red line going into it. So there's no transmission. If we then look at event B, however, we see that individual 1 is infectious and spreads it to the other individuals, 2 and 4 in event B, who then themselves become infectious. So, and then they recover after some time. So this epidemic or outbreak comes to an end when there are no longer any active infections. So there are some key parameters in this model. So there's the population size in this model. In this example, it's 1 through 10. It's 10. However, for our purposes, in the simulation we run, it's been 1,000. There's also some number of initial infectors. In this case, it's also 1, and likewise in our simulations, we also use 1 initial infector. Furthermore, there's the event size, rate, and the transmission probability within these events, which are further parameters we can treat. And in this case, so we have an event size of 3, there occurs some rather regular rate. There's a guaranteed transmission in this case, in this example, just for the sake of clarity. But in general, this is not guaranteed. So we could come into contact, didn't want to say, and there would be no transmission. The important, and then after some time, these individuals will recover. The important thing to remember is that these parameters are kind of stochastic. There's some variety, some variation in how, for example, how long exactly individuals will be infected. So one of the key things we talked about is this infectious period. Is how long are people infectious after they being told? How long do they remain infectious after they've contracted this pathogen? So we look here at the exponential distribution, which we mentioned before. And this kind of says like, oh, we have the time here on the x-axis, on the horizontal axis, which kind of denotes how long, which labels how long people will be infectious. And then on the vertical axis, what proportion of people will have this infectious period. So we see that a lot of individuals will have a very short infectious time, some individuals will have a longer infectious time, and a couple of individuals will really have quite a substantial infectious time. And then we compare this, and then there will be some mean or average infectious time. So we would compare this with the case where we have a constant infectious time, where every individual is infectious for the same amount of time, meaning there's no variation between individuals. So we're looking at 2 different cases here. The case where we have individuals with varying infectious time, and then to enable these comparisons, we set these to have the same average.
So the aim is to determine if constant infection times more consistent forecasts in the listener's model as is the case for the standard and we do this by performing numerical simulations of academic outputs.
So, this is, here we've run 10,000 simulations and looked at different outcomes. Specifically here you can see the final size. On the left-hand side we have this varying infectious time. It's exponentially distributed, but it's varying. And on the right-hand side we have the constant case, where everyone is infected for the same amount of time. Now, it might not be very clear what I'm trying to indicate here, is that in the right-hand side you see around 60% of simulations do not result in any major outbreak, while we see a larger, roughly 70% probability of there being no major outbreak in the left-hand side. So what we see here is some kind of difference between these exponential and constant case, and it is that one later. Similarly, we look at here, we see on the horizontal axis the R naught values, roughly how infectious is this disease, and then on the vertical axis we see the likelihood of there being some major outbreak. And we notice here on the right-hand side, for the standard epidemic models, as the disease becomes more infectious, we can almost guarantee that there will be major outbreaks. While, for this mixing group model, this novel model that we are examining, we see that it converges to something lower. So even for very infectious diseases, we cannot guarantee that there will be an outbreak, which is quite an interesting and frankly unexpected result for us. We can also look at the fraction of individuals infected over time. Again, on the left-hand side we have the varying case, and on the right-hand side we have the constant case. In the constant case, there's a sharper peak here, as you can see, meaning that there will be more strain on our society, and we will also expect to see more hospital beds occupied in case it was of such nature that individuals would be hospitalized for diseases. So, to summarize the results, we have that the constant case, where everyone's infectious with the same number of period of time, yields a greater probability of major outbreaks, and that the final size of the major outbreaks does not depend on the specific distribution. And in fact, finally, the constant case gives a sharper spike in the number of infections. So, the aim of our work here has been to really provide a theoretical comparison of these models and examine the underlying assumption, namely that pairwise mixing in these standard models, by comparing it with a newer model where this assumption is broken and instead look at pairwise mixing. There are some implications of this, namely that the distribution of infectious period plays a significant role in determining the probability of major outbreaks, not just in the standard models, but also in generalized models, which would seem to suggest that there is some form of general phenomenon which we would expect to see in different models, And that the standard, further, we see that the standard mathematical assumptions about exponentially varied infectious pattern kind of underestimates the strain we would see on healthcare infrastructure by providing a lower peak number of cases. And now you might have the question, why so much talk about these infectious time distributions? Here on the left-hand side, we see the exponential distribution, and on the right-hand side, you see what might be considered a realistic distribution. Now notice they're very different, right? So the reason we look at other distributions is simply because some are more realistic than others. On this left-hand side now, we see a kind of bell curve shape of the normal distribution, which is closer to the state of constant infection period. In fact, one can say that no one really believes that this infectious, exponentially distributed infection period mimics reality very well, but it is chosen instead for reasons of kind of mathematical convenience, you might say. However, this constant period, infectious period, is closer to reality than the varying infection period. And in fact, the varying infection period provides a kind of best case scenario, while the constant case provides a worst case scenario. And then by having the best case and the worst case scenario, we can say that even if we don't know exactly what the characteristics of the specific disease are, it will be somewhere between these two bounds. So, in conclusion, the examine these underlying assumptions of pairwise mixing by comparing it to a more novel model where we do not have the same assumption. And we have the results that the mixing model, the model, behaves very similarly to the standard model, but even for larger R naught values, more infectious diseases, we can, however, not guarantee that there will be major outbreaks. So future work would likely go into why then does this happen? Why can we not guarantee outbreaks for more infectious diseases? That would be done by tweaking more of these parameter values and examining the model closer, which is something we have not done because these models do take quite some time to run, and we've simply not had time to examine the impact of every single parameter combination. So finally, this presentation will not be complete without us expressing our greatest gratitude, foremost to our supervisors, Juli and Tom, who have been incredibly helpful, not just in guiding us, but in letting us think what we want to research. And then, of course, the partners to RAISE, AstraZeneca, and Pakistan State Joseph, and the school research, which we would like to thank for this incredible opportunity and these 4 weeks doing research. And then finally, we would like to thank our deepest gratitude to RAISE and the organizers and other participants for these incredible 4 weeks. So thank you so much, and we hope you enjoy.
Yes. I know I'm a bit early, but I didn't know how long it takes. So we have a summertime table now. Some lines don't read from Robert. Okay, thanks. I think my next fit test.
On these two first rows, there will be students. So.
Okay, there we go. Oh, there is something.
So this is an example of the series model. We have 10 individuals around 1 through 10 mixing events labeled A group. We have here the red lines are infectious individuals, the black dashed lines are one which is infectious individual in the one Christmas disease.
Ja, det är en sån
Finally, it ends whether no longer any infectious individuals.
inte så långt ut som det finns ljus. Sen det svarta vet man inte vad som kommer. Båda tider.
Hi, thanks.
I'm good, thank you. It's exciting to present. A bit nervous.
I guess. Well, it's a nice room, and I'm sure you're well prepared.
Thank you. I try. If there are mistakes in what I say, I apologize in advance, but I try my best.
If you're completely lost in the Q&A, I can answer, but I'll let you answer first.
Thank you so much.
Ja, just det. Nya platser.
Ja.
Ja, men den kommer inte upp på datorn.
Varom?
Kolla, den är fast.
Nej.
Vi vet inte vad som hände. Jag är rädd för att ta bort någonting eller förstöra någonting.
Vem var det som fixade det, Alexander?
Alexander, ja, men han är inte här just nu. Ja.
Det blir så varmt.
Okej.
var mitt påstående. Jag känner ingen liknande.
Men hon sa specifikt. Nej, det är lite problematiskt, men de kanske känner igen oss. Kanske. Det blir så.
De är två och de står emellan de här. Ja, det är han. Han har jobbat så. De presenterar tillsammans.
Ingenting rör sig. Eller rättare sagt, kameran funkar men det dyker inte upp på datorn. Om jag bara, ja.
Det tog många timmar. Automatsystemet funkade ju ett tag.
visa live nu va?
Ja, jag läste det.
Vad hände?
Jag vet inte, men jag bara tog bort kamera, liksom instansen jag var gästuppdatering till. Och det är komplicerat.
Det är 11 nu som kollar. 11 som kollar.
Det måste vara oss. Ska vi vakta på saker?
Nej.
Ja.
Okay, it seems like we've all settled down. Welcome back from the break, and I know we have some new people in the audience as well. So, brief safety run through again. You have emergency exits on both sides, and in case of emergency, the assembly point is outside the main entrance of the Ethnographic Museum, which is across the street from the main entrance to the Science and Technology Museum. So let's get back into the presentations, and our first presentation now is by Benjamin Henriksson and Juli. Benjamin studies at UWC Adriatic in Italy, where he takes part in activities like sailing and model UN. Juli studies at Campus Victor Rydberg here in Stockholm, and where she's active in both the Chess Society and the school newspaper. Their project is about modeling epidemics. Welcome up, Benjamin and Juli.
Hi, my name is Julina.
I'm Benjamin.
We have conducted a project on epidemic modeling under the supervision of Professor Tom Britton and Dr. Donnie Chang, titled The Role of the Infectious Period in Stochastic Epidemic Models, which is quite a mouthful, but that's also why we're here presenting today.
So, just a quick run through of the contents. We'll begin by an introduction to epidemic modeling and kind of the role of epidemic modeling in epidemiology. We'll then have a look at some of the most common epidemic models and ways of thinking about this epidemic, namely the so-called SIR models, and then we'll move over to the standard models in the field, what we kind of call the standard stochastic models. Don't worry if you don't understand what that means, we'll get to it. And then we cover something called the mixing group model, which is a kind of novel model introduced 2 years ago, and the kind of main thing we examined really in our report. And then we briefly discuss the infectious period, which is how long does an individual remain infectious after they've contracted some disease, and what impact will this later then have on the unfolding of the outbreak. So we present our results, which are numerical simulations conducted using these modes. We discuss these results and kind of put them in some broader context, and then we finally give some brief concluding remarks. So, epidemics and pandemics are something we've likely all heard quite a bit about in recent years, and there's a notable difference between epidemics and pandemics. Namely, an epidemic is some outbreak of a restricted size. It's contained to some degree, be that in a community, in a city, or in a country. While pandemics, pan being the ancient Greek of everything, is kind of are omnipresent in some sense. So the recent coronavirus outbreak was a pandemic, while the Ebola outbreak from 2013 would have been an epidemic. And what we're trying to do with these epidemic models is we're trying to say that even though we have different diseases, because these diseases are not just biological, the spread of these diseases are not just biological phenomena, but also sociological ones, we can say that even though we have different diseases, they would have some sort of similar spread dynamics, and we're trying to speak to these dynamics. And then, to give an example, we have Ebola, which was discovered in 1976 in an outbreak in the Congo, if I recall correctly, and then followed up by a second one in 1979, whereupon for 14 years there were no outbreaks. There were no outbreaks and no recorded cases, and then eventually in 1994, there were some flare-ups and minor outbreaks, culminating in a major outbreak in 2013 where roughly 30,000 individuals became sick, which is roughly 10 times as many as the second largest outbreak of Ebola. And the kind of question we could speak to in this case is, why would this happen? Why can we discover a disease which suddenly seems to disappear for 15 years, only to recur in smaller sporadic outbreaks, and then culminate in some very large outbreak? And then we here are kind of concerned with mathematics, and we're not biologists, really. And then you could ask, why? Why does mathematics become useful in epidemic modeling? And specifically, what we're thinking is that when we consider people in aggregate, they behave sort of predictably. While it might be very difficult to see or to predict how some individual might behave over some period of time, when we consider groups of individuals, these are generally more predictable. So you might think of a workplace. While some specific worker might not come in one day, the workplace as a whole will continue to meet and congregate, and we could then see some form of transmission in these events. What we do then is we take some kind of key parameters of these models, of these diseases, such as the basic reproductive number, which is, roughly speaking, how many individuals does a normal infected individual, so if I'm sick, how many will I infect? That's kind of what R0, the reproductive number, tells us. And then we also might discuss something called the transmission probability. So if I'm sick and I come into contact with Julina, what is the probability she will contract this disease from me? And then what we try to do with these things, with these parameters and these models, is we try to estimate the probability of outbreaks and the size of these outbreaks when they do occur. And then also we can look at other things like the peak number of concurrent cases. So what would the strain on society be when the outbreak is at its worst?
So it's impossible to create a model that encompasses all of the complexities of an epidemic. There's simply too many variables to consider. And so a model is a simplification of reality and make different assumptions. And one such assumption is that of the SIR models. In the SIR models, the population is split into 3 different compartments: susceptible, infectious, or recovered. And you're recovered with immunity. This model also assumes a closed community. So there's no instances of births or deaths in the population or migration. So essentially there's only 2 possible transitions, from susceptible to infectious or from infectious to recovered. For example, if Benjamin here is infectious and I'm susceptible, and we get in contact, then there's some probability that I in turn get infected and become infectious. and I will then in turn infect other people in the population, and then after some time I will recover. There are also other compartmental models, such as the SEIR model, susceptible, exposed, infectious, and recovered. So there's some incubation time or latent period before exposed individual themselves become infectious. Then there's also diseases such as the flu, which can be modeled with a SIS model, since there's no immunity. So you're susceptible, then infectious, and then susceptible again. And one of the most common epidemic models are the standard stochastic epidemic models. And these models are stochastic. And this means that there's some stochasticity or randomness induced in these models in order to sort of emulate the intrinsic role that randomness play on an epidemic outbreak. So consider, for example, what if the first COVID-19 subject would have never had any interaction with other individuals during their infectious time? There's always this randomness in epidemic models or in real world epidemics. And furthermore, the standard stochastic epidemic models make the following assumptions. The first of which, transmission occurs pairwise, so between pairs of individuals, more specifically between susceptible and infectious individual, and then it also assumes a homogeneous community, so which means that it's assumed that every person in the population is kind of equal, and there's no distinguishable difference between individuals. So during COVID-19, we talked about certain risk groups who were more susceptible or vulnerable to the disease. But that is not the case in these models. And the last assumption is that of homogeneous mixing. So it's assumed that people have contact with each other at equal rates, or that, for example, that all of you in this room, it's assumed that you have equal contact with each person in this room. Then there's also the more novel mixing groups model, which poses the question that what if transmission occurs in groups instead of pairwise? This model was introduced by Frank Ball and Peter Neal in 2022 in a paper called An Epidemic Model with Short-Lived Mixing Groups. So unlike in the standard epidemic models, individuals are randomly selected and meet in groups of different sizes, and transmission only occurs within these groups. And the rate and size of mixing groups can vary. So this is an example of an epidemic outbreak with the mixing groups model. Here you have 10 susceptible individuals numbered 1 through 10, and events or mixing events labeled A through G, with one infectious or initially infectious individual, the index case, and infectious individuals are visualized with a red line. Then the epidemic ends when there are no longer any infectious individuals in the society or in the population. This model has some key parameters. First, the population size. In this example, we have a population size of 10, but in our simulations, we use a population size of 1,000 individuals. And then you have
a number of initially infectious people, which in this case and in our model is 1. You also have an event size, which is usually random, but here for the sake of simplicity, it's constant at, we have a constant event size of 3 individuals. And then there's an event rate, and a transmission probability. In this case, the transmission probability is 1, so it's guaranteed that individuals attending the same event will become infectious if there's another infectious person in that group. And then lastly, you have recovery time, which is time until or your infectious period. And all of these variables are stochastic, so they are random, which is important for the sake of our project.
So one of the things we think about is the infectious period. That is, how long after someone has contracted some pathogen or disease do they remain infectious for? In these kind of standard models, we often assume that if there are more infectious individuals, we'll see more recoveries during some time, and we'll have people recovering at a sort of proportional rate to the number of infectious individuals. And this actually, this very subtle assumption yields a specific distribution on the periods that people are infected. So everyone is infected for some differing period, and we'll see a lot of individuals who will be infectious for a very short period of time, while we'll see fewer but more, some individuals who are infected for a longer period of time, and then we'll see very few individuals who are infectious for quite a substantial time. And then with this distribution, there will be some average infectious time that the average infectious individual, remains infected for. So one thing we can compare this to is the case where instead of varying this time between each individual, we can think about what happens if there's some constant infectious period, i.e. it does not vary between different individuals. And that gives a different scenario. So then we compare them when they have the same infectious period. We can compare this case where where everyone is infectious for the same period of time, and it varies, we say exponentially, it doesn't really matter what that means, but it varies exponentially between individuals. We can kind of compare these cases. And then it's been shown for these standard models that the constant case is kind of a worst case scenario when it comes to the probability of causing major outbreaks, while the exponential case likewise is a kind of best case scenario.
So the aim is to determine if constant infection times have more pessimistic forecasts in the mixing groups model, as is the case in the standard epidemic models. And we do this by performing numerical simulations of epidemic outbreaks and changing the parameter values.
So here we can see the outcomes of, we've run 10,000 simulations with the parameters R naught is equal to 2, so we roughly expect that an infectious individual will on average infect another 2 susceptible individuals, and we have set the infectious time to be 4, so that could be 4 days, 4 weeks, or 4 months. We don't really specify it. It's simply 4 for our case. So we see here on the left-hand side the kind of standard case where we have some varying infectious time, and we have the number of simulations on the vertical axis and the final epidemic size on the horizontal axis. So what we see here is there have been quite a few simulations where around a bit more than 800 individuals have contracted the disease, and there are quite a substantial number of cases also where the disease has instantly petered out. You could think about, for example, the initial individual never comes into contact with anyone else, thereafter recovers, and hence the epidemic ends without any form of major outbreak. Similarly, we have the same graph for the constant case, and what's interesting to note here is that in the constant case, we have that roughly 60% of simulations we never have any outbreaks occur in these cases, while we have a greater proportion, almost 70%, for the exponentially distributed case. So in some sense, when we have this varying infectious period, we see a lower probability of having major outbreaks. So we can look at this for this probability of having major outbreaks for different R0 values. So roughly, as the disease becomes more infectious, how does this change the probability that there will be a major outbreak? On the right-hand side, we can see the kind of standard stochastic models, and there we see that as the disease becomes more infectious, we can almost guarantee that there will be a major outbreak, while in the case for this generalized mixing group models, where we don't have pairwise transmission, but instead have group-wise transmission, we see that even as the disease becomes more infectious, it does not guarantee that there will be a major outbreak, which was frankly quite an unexpected result for us, but nevertheless shows that there are some important characteristics of these assumptions that have been made when we assume that we only transmit the disease pairwise. We can also look at the number of people that have been infected over time. So here we have all of these 10,000 simulations kind of shown on the same graphs. So you see some kind of more opaque outliers here, but a very strong central tendency where we see as time progresses, we have more infected individuals, which then peter off. And then again, on the right-hand side, we have the constant case where everyone's infected for the same period of time. And on the left-hand side, we have the case where the infectious time varies. And we can see that in the constant case, where everyone is infectious for the same period of time, we have a sharper peak. It goes higher than it does for the varying case. So in some sense, these different assumptions will also yield different results regarding the number of peak infectious cases, which would be important if we were to look at, for example, the strain on healthcare infrastructure during one of these outbreaks, where we would expect some proportion of these individuals to require hospitalization or some sort of healthcare. And if we had simply more cases at the same time, it would be more difficult to accommodate this. So, a brief summary of the results. The constant case, where everyone is infectious for the same period of time, yields a greater probability of major outbreaks. The final size, however, does not depend on whether this infectious time is varying or constant. So we expect to see the same average final size of major outbreaks in either case. And however, the constant case yields a sharper spike in the number of infections. So we see a greater peak strain on society as a whole. So the aim of our work here has been to kind of provide this theoretical comparison of these two epidemic models. It's been to examine the underlying assumption of pairwise mixing in these standard models and kind of looking at what does this assumption actually mean and what happens if we change this assumption. And the implications here we'll come to is that even in this general case, we have that the distribution, that how this infectious period, how we think of it, still plays a significant role in determining the probability of these major outbreaks. Furthermore, the standard mathematical assumption of this kind of exponentially varying infectious time underestimates the strain on the healthcare system in comparison to the constant case. So, we've talked a lot now about these different infectious times, and then a natural question would be, why care? Why bother with these different infectious times? Here we have this kind of exponential distribution we showed earlier, and here we have something that would be considered a more realistic distribution. So we see infectivity over time. Very few individuals are infected for a short period of time, but most individuals are infected for some longer period of time, with quite a sharp peak here at around some mean time. So simply, the reason why we look at these different distributions is because, well, some are more realistic than others. And here we see this kind of standard bell curve shape, which we see kind of more strongly resemble this realistic case. And in fact, when we're looking at this constant infectious period, we're kind of taking the edge case, the most extreme case, where this bell-shaped curve has kind of converged almost into a very vertical peak, and everyone is infected for the same period of time. So, to kind of summarize here, some are more realistic than others, but actually no one really believes that this exponential distribution mimics reality very well, but it is chosen for reasons of mathematical convenience. It makes it, we get some nice properties out of it if we're trying to show certain results, but it might not be that realistic. So, but this kind of constant infectious period case more closely resembles reality than we would see in the exponential case. Furthermore, this exponential case is kind of the best case, while the constant case is the worst case. So even if we do not know what this specific infectivity curve will look like for a specific pathogen, we will see that these kind of create the bounds on the probability of outbreaks. So we'll see that it'll lie somewhere within these bounds if we're thinking about some unknown disease or a disease which we don't completely understand. So, in conclusion, the scope of our work has been to provide this theoretical comparison of these models. It's been to examine the underlying assumptions of these standard models, specifically in regards to this assumption of pairwise mixing, that all transmission simply occurs in pairs rather than in groups. And we've come to the conclusion that the mixing group model, which I described, generally behaves similar to the standard models, but there's the important difference that even for larger R0 values, so for more infectious disease, we do not see a guaranteed major outbreak, which is quite an important difference between these models, and something which does not seem to hold as we generalize these models. And the future work would kind of go into, if one was to perform future work, it would likely want to go into why we see these lower outbreak probabilities and what causes this kind of this uncertainty in whether there will be an outbreak, even for more infectious diseases. So that is our project, and of course this presentation would not be complete without us expressing our greatest gratitude to our mentors, Donny and Tom, who have been guiding us throughout this entire project, not just in matters of theory, but also in allowing us to really explore what we want to explore. Furthermore, we would like to thank the race partners AstraZeneca and Tagestan Stiftelse för utbildning och forskning for their gracious support of this event. Also School Research, which is a Finnish organization. And then finally, we would like to thank RACE, the organizers, and everyone else here today for this incredible experience these past 4 weeks.
Thank you so much, Benjamin and Jelena. Are there any questions in the audience?
Om vi fick chansen att fortsätta att titta på det här framöver i fördjupad forskning, skulle ni tänka er att göra det? Och vad skulle ni i så fall titta på?
Då var det här, vi såg att även för mer smittsamma sjukdomar så kunde vi inte garantera att det skulle ske större utbrott. Och det vi skulle då, vi forskade så varför det sker. Vi nämnde ganska många parametrar, men det var ganska få vi faktiskt varierade. För de här modellerna är ändå relativt beräkningstunga. Så vi hade inte tid att köra dem för alla olika parametrar. Så det som fortsatt arbete då borde fokusera på är hur liksom påverkar de här andra parametrarna de olika resultaten vi ser från modellerna. Så som sannolikheten att det finns ett större utbrott.
Ni tog upp att den här modellen inte nödvändigtvis är certifieringssystem, men hur bra överensstämmer de med verkligheten?
Så det man brukar göra i modeller för verkligheten är att man har ofta så här någon form av geografisk data. Det vill säga att vi har olika små gemenskaper här som där det sker smittspridning och sen kollar man liksom för att stå framåt och här. Ofta används då de här modellerna på en mindre skala där man liksom vill utforska så här, okej, det här med att alla träffar alla nästan hela tiden kanske inte håller för samhället som helhet, men i så här smått sammanhang så kan vi göra det. Så man brukar använda de här som delmodeller i större, mer realistiska modeller.
Yes, tack Benjamin. Swedish. Thank you Benjamin and Jelena for your presentation. Thank you. Okay, next up is Marie Brazier. She studies at Lowell High School in San Francisco and has competed internationally with her school robotics team. She is now going to present her project about model-based testing. Welcome, Marie.
Hi, I'm Marie, and today I will be talking about the optimization of model-based testing. So I'm sure we've all used software systems at least once in our lives. And in order for these systems to work as safely as possible and to be qualitative, they need to be tested. And in software, we call that software testing. And there are different types of testing in software. However, I will be talking about 3 main ones. And those are unit tests. Unit tests are small tests that test system codes, so small parts of the code, and are often used by businesses because they allow the collaboration of multiple workers who can then set their small code segments together and test them so that the whole code at the end works. There are also system tests, which are tests that test entire systems. And so they are much larger to write and take more time to modify. They are very useful, however, and often used by businesses. However, they're difficult to use because when multiple people are working on a code, they have to modify the code all the time. And in system tests, all these small parts that are modified need to be fitted for the tests. So they are quite difficult to work with sometimes. And lastly, the most important one, which we are focusing on for this project, are model-based tests. And model-based tests use system tests to generate unit tests. I will get further into that later. And for the purpose of this project, I will be calling them gratis tests because they, in the system that we're using, they are called gratis tests. Model-based testing. Model-based testing is made out of 3 different steps. And those steps are, first, the model. First, the model is created by a human writer who takes from systems descriptions of tests and puts them in a model. And these descriptions can be visualized as a recipe. So if you take ingredients from a recipe and then put them in the model. In the model, so in these descriptions, there are an input and an expected output. With this information, we move further into the transformation part. In the transformation, the computer takes this expected output and the input that was given and tries to generate and find and create a test that will be able to match these inputs. So then after that, the tests are executed and they test small parts in the code individually, and there are a multitude of them, of the tests, and they are able to, and the computer is able to compare the outputs, the expected output, to the real output. If these do not match, then there is an error in the code. So they are quite efficient tests. For our project, we have been using a system called Modbat. And Modbat is a model-based testing system, which is very good for testing software APIs. And it is also based on annotated finite state machines, which means that it is finite state machines are very good to execute the code by comparing and using the inputs that was given, and to create simulations and tests to see if the output matches the input matches the output and finds path with this. And in order to optimize the total amount of time that it took to run these model-based tests, which are very large and can take a lot of time, we had 2 different steps. We had first the transformation, which, as I said before, is we took descriptions from system tests that already existed and converted and put them in models in order for the computer to generate tests given these descriptions. And when we had these tests, we ran them across multiple versions, and the versions were from different dates, so they go back multiple years, and they have different days as well that they were tested, where a different amount of tests was in each version. So we compared system tests to gratis tests, which are model-based tests, and we converted these system tests to Gradle tests. This means that over time, the amount of system tests decreased, while the amount of Gradle tests increased. In the next step, we tried to optimize the actual amount of time that it took to run these tests. And we did this by grouping similar tests into the methods. And so every time a test is run, classes and libraries have to be reinstalled every single time. And that takes a lot of time, and developers do not want to wait for that. So what we did is we took all the tests that required the same classes and libraries, grouped them together, so that all the classes could be installed once, and then the test could be run individually, taking much less time. And so what we did is we ran these tests across the different versions and compared the results that we got from when there were more tests and when there more Gradle tests and when there were less Gradle tests to see how time changed and if the grouping method worked. And what we could see with that was first this graph, which represents the time that it took to run Gradle tests across time. So on the y-axis, this one, you can see that the oldest version that was run is on the very top, and as we approach the present, we get closer to the 0 value. And if you can, and on the x-axis, you can see the total amount of time that it took to run these tests in milliseconds. And you can see that as we get closer to the present, the amount of time that it took to run the Gradle test increased. But that is normal, because, as I said before, the amount of Gradle tests that were created and are in each of these versions increases over time. And as could be expected with the grouping method, the amount of time that it took to run the older versions of the test was not proportional to the amount of time that it took to run the newer or more Gradle tests, which shows that time was optimized in the process. Another very important plot was this one, which shows the average time that it took to execute both Gradle and system tests. And so over time, as I said before, system tests were converted into model-based tests. So the total amount of time that it took to run all these tests did not change over time. And we can see that there is a constant decrease in amount of time that it takes to run these tests, which shows that as more Gradle tests were added to the system and more system tests were removed, it took less time, although the amount of tests was equal. So as you can see, the versions become newer if farther back, so that means there are more tests. And you can see the total amount of time that it took on the y-axis. Of course, there were some inaccuracies in the measurements of time, because we ran these tests on a computer, and in computers, there are always systems running in the background. So when we try to measure the time that it takes to run a certain system, it is always affected by background systems running in the background. And so that was one of the main problems that caused inaccuracies in the measurements. Another error that could have occurred is the number of iterations per test. This means, so an iteration is how many times a test is run in itself. So the more iterations there are in a test, the larger it is. So it takes more time to run these kinds of tests. And in this graph, you can see that although approximately 70 tests took only one iteration, so they were very small tests and didn't take much time, we have larger tests here that took thousands of iterations, which made them much larger, and so they took much more time. And we can see this, that this caused some errors. For example, in the beginning of, or between the first version and the second version, when there is this unexpected increase in time. So, to conclude, what we can see is that model-based testing consists of 3 different steps. We have the creation of a model. A model is a set of descriptions that can then be used in the transformation process by a computer to create unit tests. And then, with these unit tests, these tests are executed, and the computer can then compare the results or the outputs from the given output, so the one that was expected by a human writer, and then it can be compared to the output generated by the computer. And we could see that the method worked because the overall time that it took to run all the Gradle tests and the system tests together decreased as more Gradle tests were added to the system. And this shows that the grouping method worked and that Gradle tests can be more efficient than system tests. Now, you might wonder, why is this important? Well, this is important because system testing or software testing is used all the time in our lives when we use software systems. And businesses use testing, but they mostly use unit tests or system tests. And these kinds of tests use humans. So this costs time and money. And what model-based testing does is that it doesn't use human writers, or not as many. So this would be much more cost-effective. However, the time that it takes to run model-based tests is much larger than it takes to run system tests and unit tests. So with this experiment, we were able to show that it is possible to minimize the amount of time that it takes to run model-based tests, and therefore, this could be a testing system or a testing tool used later in the future. However, today, we can still know that system tests are more effective than model-based tests, but hopefully, later in the future, we will be able to show that model-based tests can be used as well. I would like to acknowledge my very dear mentor, Cyril Artho, for his help in this project and for leading it. And I would also like to thank Race for Excellence and their partners Magn Bergvas och Beijer Stiftelsen for their support and for making this possible. Thank you.
All right. Thank you so much, Marie. Are there any questions in the audience? Yes.
How do you combine multiple libraries to a single entity?
So what we did was we used the tests that required the same classes and libraries that imported them and put them in one model. So you don't combine the libraries themselves, but you combine the different imported libraries, and then you put all the tests that require those libraries into one model. So instead of for every test to need to import these libraries once again, and every time that takes a lot of time, we initialize them once, install them once, and then we go through the tests without using as much time. Yes?
Yeah, when you say you generated unit tests, you mean you could actually look in the code and see what unit tests were made, or was it all like a black box?
So the computer uses the inputs that you've given and tries to find possibilities and paths to match the output that you gave. So it tries to match it, and then it tests itself. That's what MatBat does. It tests the tests themselves, and then can run.
Right, but actually produces code.
It produces code, yeah.
Right. Since we have no more questions, thank you so much, Marie.
Thank you.
Okay. The next presentation is by Anneli Nguyen. She competes in Taekwondo, but she's also interested in the natural sciences, which she studies at Tyvärr in Helsingborg. Her project is about the effect of heat shock on leukemia cells. Welcome, Anneli.
So, hello. So today I'm gonna talk about the effect of gene expression in K562 cell line after heat shock. So, gene expressions varies from cell to cell, even if it's the same cell type. And during a heat shock, when the cells are exposed to more than 42 degrees, the genes start to change, the gene expression. Yes, there has not been many studies about the cells by themselves, but there are more studies about the cells in general and how it changes. But now we're going to dive in further about that. During stress, the cells get damaged in the cellular structure as well as important functions to the cells. What's special about heat shock is that it also makes the protein misfold and aggregates are formed inside of these cells. This is the cells we use, which is a K562 cell line, a leukemia cell line called monogenous leukemia cell line. And the reason why we use this cell line is that because it multiplies very fast and it's also immortal. Yes, and the aim of the project is to look at the different the genes expressions in the cell line K562 and see if there's anything they have in common, the clusters, the groups of the genes that has changed. The methods used are single-cell RNA sequencing, which is when the mRNA is looked at cell by cell and not in total. And we also use some dimensionality reducing methods called PCA, principal component analysis, as well as UMAP. And it's because the dataset is very large of many thousands of cells and genes, so we need to make it smaller in order to easily analyze it. And the principal component analysis helps reduce big data sets into smaller ones. Yes, and UMAP is this one there, and it makes it even smaller into only 2 dimensions. And each color is called a cluster, and the clusters have something in common with each other, which they don't have with the other clusters, which is called the special genes. So the results and discussions. Here you can see 2 heat maps, UMAPs. Here you can see the control sample and the heat shock sample. When put into one, you can see that they are both separated from each other, which means that the gene's expression has changed. If it hadn't changed, it would only be one big cluster all mixed together. Now, notice that there is one cluster here at the side, which is kind of strange. It shouldn't happen. And also one at the bottom. And when looking here, you can see that it's one cluster. They all have something in common. And I dive into this and see, here are 2 housekeeping genes, which are essential genes for the cells. And you can see that the genes are expressed in all of the cells, which means that none of them are malfunctioning. Going forward to the top 10 special genes of the cluster that were separated, the big one. And you can see here, they're not really expressed in any of these, which is the thing they have in common, while they are expressed in the other big clusters here. Therefore, we can conclude that they do not have a lot of gene expression and are quite empty. Now back to this little one that is here. You can see that it's part of the heat shock cells. And it also acts like the other heat shock cells here. If you look at the other diagrams that we just had before. And then we look at the top 10 marker genes, the special genes. And the thing they have in common here is that they start with RP, many of them, which is ribosomal protein. So the thing they have in common is that they're genes that expresses ribosomal proteins. Now, onto the heat shock proteins. Here are two examples, and you can see that they are expressed mostly after heat shock. It is because heat shock genes are expressed to help the proteins that has been misfolded or been clustered together. Yes, genes for heat shock proteins. And here are two examples of genes from cluster 1, 2 of the special genes. And you can see that they are mainly expressed in the upper part, the part where it's a control sample, and almost none at the heat shocked. And when I looked into it, I could see that they had one thing in common, which is they play a role in cell differentiation. Now, the reason why they were turned off by the cells is because during heat shock, the cells are very stressed and therefore have to focus on the stress and fixing the problem. That's why the cells chose to turn off functions that are not important for the survival, which is, for instance, cell differentiation. This is called a heat map. Some of you might have seen it before from my project partner, Emily. So I'm going to take it again. So the rows here are genes, and the columns are cells. Yes, and the black color means that it's the average gene expression, while the yellow one is higher gene expression, and the pink-purple one is lower gene expression. So there's one thing that looks a bit strange with this heat map. It's this area. You can see it's almost completely black. And when I looked into some of the genes, two of them, TMEM102 and PDF, I saw that there was one thing in common. They were both tissue cell type, testis-late spermatids. It is the stage of a cell before it became a mature spermatid. So conclusion. Genes for heat shock proteins are expressed after heat shock because it needs to solve all the problems that comes with heat shock. Genes that are unnecessary for the survival of cells are turned off and not expressed after heat shock. Genes that have tissue cell type classification testis late spermatids are expressed as a reference expression level, which is the average expression level. And there are also genes that are almost empty, and they are either not expressed before nor after heat shock, except for housekeeping genes, because they're very essential. Genes that codes for ribosomal proteins changed a lot after heat shock, and they differs from the others. And further studies. Well, further studies can be to change the cell line, the leukemia cell line, with a healthy cell line to let it be more relatable to us healthy humans. And we can also substitute the cell with other cells from other organisms to see if it differs or if it's the same or how it unfolds. So what is important about learning heat shock cells? Well, the important thing is we can see how organisms react in stress. In this example, heat. And we can also see how the cells react in different environments. For instance, when it's global warming and so on. Yes, I want to thank my mentor, Serhat Aktay, for all the advices and all the help. And I also want to thank my project partner, Emily Liu, for helping me and doing this project with me. I also want to thank all the X-rays who have been reading my report and giving some criticism, both bad and good ones. And I also want to express my gratitude to Race for Excellence for giving me this very important opportunity, as well as their partners, Tekniska Museet, where we are today, as well as AstraZeneca. Thank you for listening.
Thank you so much. I'm so sorry. Are there any questions from the audience? No?
Excuse me, what did you say?
How long time take the cells to repair itself when the genes is turned off and then there is a repair time?
Well,
the genes turn on again or
I haven't really studied that part, and we analyzed more what's special with the genes after heat shock and what they have in common after the gene expression has changed. But I think it varies from how long they have been heat shocked and what kind of cells. And this also a leukemia cell, which is a sick cell, so they might also do some unpredictable things.
Right. Thank you, Amber. Next up is Daniel Seher and Jakob Hyttner. Daniel, who has previously done astrophysics research, studies at Katedralskolan in Lund. Jakob, who is also interested in astrophysics and active in various related organizations, studies at Norra Real here in Stockholm. Their project, though, is not about astrophysics this time, but rather about the magnetic properties of different materials. Welcome up, Daniel and Jakob.
Welcome. My name is Danny.
And my name is Jacob.
And today we are going to be talking about quantum materials. I'm specifically going to be talking about quantum magnetism.
Well, I'm talking about superconductivity.
We want to start this presentation off by thanking our wonderful mentors, Jasmin Sassa and Martin Månsson, who sadly couldn't be here. I hope you're there behind the camera, for making this project possible. And also the partners of RAISE, specifically Stiftelsen Europaskolan and Ulle Engqvist Stiftelse.
As well as Tage Svan Stiftelse för undervisning och forskning och Beijer-stiftelsen for providing funds to make this possible.
All right. I have a question for all of you. Have you ever heard of quantum physics? Okay. I want to make a bold statement. I want to say that most of you, when thinking of quantum physics, think of the most exotic phenomena of quantum physics, like that the world is probabilistic and not deterministic, or the Heisenberg uncertainty principle, or the superposition of a particle. But many fail to realize that quantum properties are actually around us all the time. Most people think that quantum physics is something so small, so intangible, that we cannot interact with it daily. But I'm here to tell you, that's wrong.
This is a magnet. For most of you, this is a completely ordinary object that you use to hang up papers on your refrigerator, or within your credit cards to be able to buy groceries, or within your hard drives in your computers. But magnets are far from ordinary objects, as their properties cannot be explained using classical physics. To paint a better picture, you need to use quantum physics to be able to explain why a metal like iron can create a magnetic field. So, how does quantum physics explain magnetism?
All right. So to be able to understand quantum physics using, quantum magnetism, we need to familiarize ourselves with the concept of spin. So what is spin? It's usually said that spin is the intrinsic angular momentum of a particle, which means that it's the angular momentum of a particle that doesn't actually spin. I like to describe spin as, think of a ball that's spinning around an axis. Spin is that ball spinning around an axis, but it's not a ball when it's not spinning. But at least the properties of spin are easier to understand. Spin usually comes in two types: spin up and spin down. And that's determined by how the spin is related to the magnetic field, or the field lines, or just the specified axis. So for spin up, the spin rotates counterclockwise and has a field line with the field. And the opposite is true for spin down. Why spin is important for quantum magnetism is because the spin of every particle gives the particle a magnetic moment, and combining many different particles inside of a material gives the material a collective magnetic moment. But you can also combine the spins in many different ways. Some of the most common ways are paramagnetic materials, ferromagnetic materials, and antiferromagnetic materials. So what are these three types of materials? Starting off with paramagnetic, as you can see here, paramagnetic materials is where the spins are not aligned together. It's a disordered state, sorry. To the contrary, ferromagnetism is a completely ordered state where all the spins are aligned in the same direction inside of a magnetic domain. And antiferromagnetism is where the spins are also aligned, it's an ordered state, but they're ordered opposite to each other for every single spin. But how do we know if a material is ferromagnetic, antiferromagnetic, or paramagnetic? To know that, we have to look at something called magnetic susceptibility. Magnetic susceptibility is basically a measurement of how much does a material get affected by an externally applied magnetic field. And we can plot the data that we get from magnetic susceptibility for different temperatures. And we can see that for the different materials, the graphs have different shapes. Specifically, disordered state, they don't have a critical temperature where their magnetic susceptibility drastically changes. So you can see here it just goes on. For ferromagnets and antiferromagnets, who are ordered states, you can see that there is a critical temperature where the magnetic susceptibility suddenly changes. For ferromagnets, it goes onto an asymptote, and for antiferromagnets, you can see that the magnetic susceptibility peaks at the critical temperature and then drops again. But sometimes, looking at data points, it is hard to see if the material is ferromagnetic, antiferromagnetic, or paramagnetic. It's not always this beautiful. So what do we do then? We take the inverse, or the reciprocal magnetic susceptibility plotted against temperature, which means 1 over the magnetic susceptibility. If it is one of these three states, you get a linear graph. And if you see a linear graph, you can plot something called the Curie-Weiss law against it. What the Curie-Weiss law basically tells us in this context is what the x-intercept could be analyzed as. So if you have an x-intercept that intercepts the x-axis at a negative value, you get antiferromagnetism. If it's at 0, it's paramagnetism, and if it's positive value, it's ferromagnetism.
Yes. The second quantum material we'll talk about are superconductors, and they are an entirely different beast altogether from magnetism. Superconductors are defined by two principal properties, namely losing all electrical resistance when below the critical temperature, and the Meissner-Ochsenfeld effect, which is the expulsion of all magnetic fields. In contrast to magnetism, this is an extremely temperature-sensitive phenomenon. Superconductors either exhibit all their quantum phenomena when below the critical temperature. Superconductors exhibit all their quantum phenomena in full, but above it they exhibit absolutely nothing. This critical temperature is often very low, in most cases below the temperature of liquid nitrogen. So, what is the zero resistance state? Well, although the resistivity of almost all materials decreases as temperature does, it never does as sudden as with superconductivity. When a superconductor is cooled below the critical temperature, it instantly drops down to 0, like God decided to round it off. When a material has zero resistance, it gets a lot of very strange properties. First and foremost, it doesn't lose any energy when the current runs through the superconductor, and the current can run without any voltage. This means that you can theoretically, or practically as well, create a superconducting loop, put the current within it, and the superconducting loop will continue spinning around the superconductor forever, or the current will spin in the loop forever and ever. To many of you, this will sound impossible, because it's perpetual motion. The thing is, perpetual motion is only possible within classical physics, and this is precisely how we know that superconductivity is a quantum phenomenon. You can see it like an electron orbiting around an atom's nucleus. It will travel around without losing energy forever, like the electrons in the superconductor travel around the loop. The second main property is the Meissner-Ochsenfeld effect. And if you know your physics, you understand that through Ohm's law, if a material has zero resistance, no voltage can ever be applied across it. A change in magnetic field always causes a voltage, which means the magnetic field within the superconductor can never change. The solution, if you can call it that, to this is the Meissner-Ochsenfeld effect, which is when a magnetic field is applied to a superconductor. Just stand, Mike. A current is generated across a surface. This current, because the current is a movement of charged particles, it generates a magnetic field, just like spin. This magnetic field is just strong enough to expel and counteract the applied magnetic field, curving the field lines around the superconductor, as you see here. This is what causes the incredible ability for superconductors to levitate above magnets. And if you know the Japanese Shōshinkansen trains that are currently in development, they use superconductors to be able to float and go faster than any other terrain. What did I do? Superconductors are divided into two groups, conventional superconductors and unconventional superconductors. To simplify, conventional superconductors are superconductors we understand, and unconventional superconductors is everything else. Conventional superconductors tend to have very low critical temperatures, and they are described with a theory called BCS theory. Conventional superconductors also tend to have these nice quadratic relations between resistivity and temperature above the critical temperature. Unconventional superconductors does none of these things. They can't be explained by BCS theory, at least not solely. They have no nice relation between, or at least not a quadratic relation between resistivity and temperature, and they can have wildly different critical temperatures.
Yes. So the material I'm going to be studying is called calcium, copper, titanium, ruthenium oxide. This material is a synthesized material, meaning it's produced in a lab. It's produced in extremely high pressures with high temperature. But what is interesting with this material? As some of you may have noticed, there's an X here. And this X determines the substitution of titanium atoms with ruthenium atoms. And contrary to popular belief, this X does not have to be an integer. I had one of the compounds where X equals 2.25, meaning it's titanium 1.75 and ruthenium 2.25. Now many of you may be thinking, how does that even work? Well, it's not as the chemistry we're used to. It's kind of just how much of titanium compared to ruthenium there is in the whole sample, not just in a crystal structure. The aim of this study is to see how the magnetic susceptibility and why the magnetic susceptibility changes substituting titanium with ruthenium.
Yes, the material I studied was the lithium titanate. And lithium titanate is a superconductor with a spinel structure, which is a special kind of cubic lattice structure. It's a type of crystal. Lithium titanate was assumed to be a conventional superconductor up until 2015. Then it was discovered that the magnetoresistance, which is the relation between applied magnetic field and internal resistance, shifted from negative to positive at a temperature of around 50 Kelvin. This is speculated to be due to a phenomenon called orbital ordering, where the orbitals, the path of the electrons, align in a certain way that allows current to flow differently. And that is then destroyed at too high temperatures and too high magnetic fields. Another interesting aspect of lithium titanate is the fact that although in the beginning it follows this nice conventional quadratic relation between resistivity and temperature, at some point it diverges to something that looks more linear. The aim of my study was to connect these two phenomena. Identify the point when the relation diverges from quadratic and see if that can be due to the orbital ordering phenomena, or what's thought to be orbital ordering.
Yes, and to conduct our experiments, we actually both used the same machine, but different tests from the machine. I did AC susceptibility, which is obviously much better than his test on resistivity.
We'll see you got the nicest graphs.
Okay. But how does AC susceptibility work? So here you have an intersection of the PPMS, or the physical property measurement machine that we used. The sample is put down here, and it is surrounded by superconducting magnets.
Your method uses superconductivity. You will be nothing without me.
I guess we just complete each other, Jacob.
Very well.
So the sample is put down here, and it's put on top of a lever that lowers and raises the sample through the superconducting magnets, while also running AC current through the sample. The AC current inside of the sample and the movement up and down counteracts the magnetic field in the superconducting magnets, and we get a readout. All of this while having the temperature decreased from 300 Kelvin to 2 Kelvin, and then back up from 2 Kelvin to 300 Kelvin.
Yes. My method was to measure resistivity using a method called four-terminal sensing. It's a method where you use a parallel circuit to measure voltage and current and use Ohm's law to automatically calculate resistance. And by using a parallel circuit, the lead resistance and contact resistance is minimized, which gives more exact results. To do this, we took my sample of lithium titanate and connected four pairs of nanowires to it. These nanowires were bonded manually using a bonding machine, which is a glorified sewing machine, and were about 25 micrometers in diameter. It's incredible that the camera was able to capture this.
It was because it was my camera.
Yes. So, my results. We got this beautiful graph here of the resistivity over the temperature. And the critical temperature was determined to be 11.5 Kelvin, which is identical to previous results and shows that our method was very exact. We used this data to plot a derivative function, which quite obviously has a very sharp peak at the critical temperature. So I cut away that and gotten this beautiful graph. The point of divergence, which I'm trying to localize, was assumed to be the point where the derivative was at its maximum, because the derivative of a quadratic function always increases. So we found this peak, did a linear regression of the graph up until that peak, then used some calculus to take the primitive function of that linear function and fitted that to the curve. And this created this absolutely beautiful fit that diverged exactly where I thought it would at 119.99 Kelvin, the same as that point. But what does this mean? I'm quite positive that we found the correct point of divergence because the fit was very exact, but that's far from the 50 Kelvin point of orbital ordering, or speculated orbital ordering, that we tried to, we thought would explain this. But if you look at this graph, you see that how the dependency of resistivity over temperature increases as the magnetic field does. This was done with a very weak magnetic field. And my theory is, as the magnetic field increases, the difference between these slides will increase, obviously, and the point of divergence would move back at a magnetic field of infinite Tesla. It would approach and be exactly 50 Kelvin, those points moving together.
All right, these are my results. Here you can see 3 graphs of the 3 different samples we tested from the compound with different doping. Here we have where x equals 0, meaning titanium 4, x equals 2.25, titanium 1.75, ruthenium 2.25, and here we have the other end of the spectrum where x equals 4, meaning no titanium and only ruthenium 4. Looking at this part of the graph, if you remember, we can see that it is a beautiful anti-ferromagnetic curve. And to be completely sure that it is anti-ferromagnetic, I plotted the inverse susceptibility, and then I saw that it was linear from about 100 Kelvin to 300 Kelvin. And then I fitted the Curie-Weiss law to it, and saw that I got a theta value, or an x-intercept value, of minus 283 Kelvin, which means it's anti-ferromagnetic, hallelujah. And then looking at the other sample, where x equals 2.25, we see that there's some magnetic ordering, but it's not really as sharp as in the x equals 0 sample. And when I plotted the reciprocal inverse susceptibility, I noticed that it wasn't linear. Therefore, I wasn't able to do a Curie-Weiss law fit, and determined that it does in fact not actually order magnetically. And here we can see that between the x equals 0 and the x equals 2.25, we have a vanishing effect of magnetic susceptibility in the compound. And to further cement this statement, we can look at the x equals 4. And here we see that the graph is just jumbled. We have no magnetic ordering. And well, maybe some of you may be thinking, it does look like a little bit like magnetic ordering here. But looking at the raw data, I concluded that it was just an effect of some changing magnetic field inside of the PPS machine, so it wasn't actually magnetically ordered. And we can also further cement that statement by looking at the inverse susceptibility and seeing that it's not linear at all. But what does this mean, and why does this happen? The 2 main factors for this happening is the titanium and ruthenium have different electronic properties, and also the titanium and ruthenium have different sizes. So starting with the electron properties, titanium exhibits something called localized electron behavior. What localized electron behavior means is that every magnetic moment inside of the crystal structure is separated, it's not unified. But by looking at the ruthenium, we see that it is delocalized magnetic behavior, meaning that all the magnetic moments are spread out throughout the crystal structure, throughout the lattice. And this decreases the magnetic susceptibility a lot and makes the compound not ordered. And looking at the size difference, we can see here that titanium is much smaller than ruthenium. This also makes the crystal itself smaller while having titanium and bigger while having ruthenium. And this size difference makes that the electron interactions in the sample with more titanium is much stronger and therefore more prone to ordering, while the contrast is true for the ruthenium. And we want to thank you all, especially our group that has made everything possible here, Reis, Ulle, Solveig, Arman and Linnea. And I want to thank every X-ray that has read my report and Jacob's report and helped us with everything we needed help with. And I want to direct a huge thank you for all the amazing people I've gotten the opportunity to learn during these 4 weeks. And I'm gonna miss you all so damn much. Thank you.
Thank you so much, Danny and Jakob. Are there any questions from the audience?
Yeah.
Are you able to go back to your graph when you look at the video?
Yeah.
Yeah, like looking at the derivative, it looks an awful lot like there's some discreteness going on. Like, how do you explain that?
I don't, right, at the moment, but I agree with you. Alas, there is a lot of noise here, and I would say that the discrete steps are within the margin of the noise, but I agree, there looks to be discrete jumps here, and that is actually something I think we should conduct more research, but currently there is no model to explain this, but it's not unreasonable that resistivity is quantized as it is a quantum phenomenon. And one.
Do you think we can use the Meissner-Rosenfeld effect for creating, let's say, hoverboards?
Well, I've actually thought about this a bit. The thing is, the Meissner-Rosenfeld effect, when the magnetic field is too strongly applied, it will become more favorable from an energy standpoint to increase the temperature and stop superconducting. And I think a hoverboard, if it was cooled down, which is a difficult technical aspect, I think the smartest way to create a hoverboard would have to have a superconducting floor and the magnet on top of it, and jump on the hoverboard, and then you can glide only across the superconductor. More of a theme park ride than a vehicle, but still fun.
I'm just going to add, we were supposed to have a demonstration here of the supermagnet actually levitating, but sadly our mentor got sick, so she couldn't even be here. So, but
we hope you're there.
We almost made you a hoverboard today. Anthony?
Sorry. This blue line in this graph, is this raw data or did you use some type of filter?
No, this is raw data.
Okay, thank you so much, Danny and Jacob.
These peaks are really significant for proteins. Moving on, we also see a characteristic glycosidic bond in this peak right here, showcasing that there are polysaccharides within the material as well. And then lastly, we have this peak, or these peaks right here, showcasing normal bonds within both polysaccharides and proteins. Hence, we can come to the conclusion that the materials probably both contain polysaccharides and proteins. But what's even more interesting are that no further peaks are shown in the spectrum, thus no new bonds between the polysaccharides and the proteins have formed. So the conclusion is that all the materials produced using biopolymers showcases lower densities compared to the density of the actual plastic sanitary pad. Furthermore, all materials showcases better absorption for defibrinated sheep blood compared to the absorption of saline. Thus, these materials might be better potentially suited as an alternative to the lightweight plastic absorbents currently used in menstrual pads. Considering this, future studies could aim at trying to evaluate how non-defibrinated sheep blood affects the absorption as well as the porosity of the materials to better and find a solution that better mimics menstrual fluids. It might also be advisable to try to mimic the structure right here, trying to manipulate the sizes of the pores to create larger sizes that will facilitate absorption, but also smaller pores that will prevent leakage. So even though the materials that are produced showcase the better absorption for sheep blood, we should not forget the aim of the study, to try to replace the plastics currently used in both diapers and menstrual pads. Because future generations should be able to use diapers that do not affect the environment as much as they are right now. I want to thank my excellent mentor, Antonio Capesa, as well as Mercedes and Anthony for all the assistance in the lab. I thirdly want to thank Race for Excellence and its sponsors, Stiftelsen Bengt Lindqvist Minne and Binger Stiftelsen. And obviously I want to thank all the X-rays for providing assistance with the writing process. Thank you for listening.
Thank you so much, Henrietta. Are there any questions in the audience? Yeah?
I would like to thank you about the presentation and the purpose of the study. So actually I have 3 questions and maybe recommendation. So the first one, how do you think about the sources of raw material? Like if it's the commercial product, where
with the polysaccharides and proteins. And we use byproducts from the agriculture, meaning that the products that we use are like rest products. So instead of throwing that away, we can use that to produce the lightweight absorbent products, and thereby kind of closing the circle and preventing using new materials. I think previous studies have shown that some of the materials are antimicrobial and they're non-toxic, but I think it would be advisable to do further research, and if we're going to use these products in actual menstrual pads, we have to conduct more research and testing the safety of the products and make sure that, as you said, no bacterials are produced. Yeah. No worries. Yeah?
Why is the absorption of blood better than the research?
Well, it might be because of the amount of particles within the solutions, because the absorption is due to osmolarity, and when you have more particles, that changes how much will absorb. and saline, containing both sodium and chloride, changes the amount that is absorbed. Yeah?
Do the raw material on the polysaccharides and protein absorb the humidity from environment?
The what?
Absorb humidity from environment?
That is a good question. I have not tested that, so maybe that is another thing that future studies could test. But I mean, if you can absorb saline, it can probably absorb water and things from the air as well.
Okay, seems like there's no more questions. Thank you so much, Henrietta. Okay. In our last presentation, before the break, we're going to learn more about a mysterious astronomical object that Sofia Nordblom has been studying. Sofia, who studies at Tekniska Museet in Gothenburg, is very interested in astrophysics and has previously taken part in both camps and summer school on the subject. Welcome up, Sofia.
Hi. My project is about determining the classification for an unknown astronomical object. The object is called SN 2022 RCE, and we've used spectral analysis for classification. My name is Sofia Nordblom, and I've been working together with Dr. Priscilla Pesci at Stockholm University Department of Astronomy. In August 2022, one of ESA's telescopes received signals from this object. At first, it was classified as a supernova, but as time went on and more information was collected, the scientists were no longer as sure about the classification. A supernova is an explosive event which occurs at the end of a star's life cycle. It happens when all of the mass implodes into the center of the star, and which is then followed by a huge explosion. When classifying supernovas, we're typically looking at light curves, and this is an example of a very typical supernova light curve. On the y-axis, we have the magnitude, which is the strength of light. On the x-axis, we have the time. We can see that this is a typical supernova because of the sudden increase in magnitude followed by a sudden decrease in magnitude. Then there's a steady decline in magnitude. This object has a light curve which looks like this. We can see that it has a peak here, but we can also see that it's not that similar to the typical supernova light curve. For example, it's a lot more bumpy and doesn't have that same steady decline. The reason that it was first classified as a supernova is that we in the beginning only had access to this information, and here we can see a very steady decline. If the object weren't to be a supernova, one could theorize it being something called an active galactic nucleus instead. An active galactic nucleus is a black hole in the center of a galaxy. It is active, which means that it's accumulating materia and expanding. This results in a light curve that is a lot more steady. Further, we know that it's a lot more long-lived than the typical supernova would be. And that is another reason that we are unsure about the supernova classification. But in order to determine whether or not this object is a supernova or an active galactic nucleus, we look at the spectral lines. Spectral lines are emitted from an object when an excited electron returns to its original energy level. Then there are spectral lines at specific wavelengths which are emitted depending on the object. The spectral lines for this object looks like this. We know that in both supernovas and active galactic nucleuses, we have a presence of hydrogen beta lines, oxygen 3 lines, hydrogen alpha lines, and nitrogen 2 lines, and those are marked here. What I've done more specifically is that I've been looking at the area under these peaks, and then I've been implementing these areas into something called a BPT diagram. A BPT diagram is a diagram which utilizes the ratio under the spectral peaks in order to determine the nature of an object. So when we perform these measurements, we implement them into this diagram in order to see in which region the measurements fall. If the data points were to fall in this region, we would be able to draw the conclusion that the object is a supernova. If the measurements were to fall in this region, we would assume it's an active galactic nucleus, or an AGN. And just for reference, a liner is a different type of active galactic nucleuses. We hope that the measurements don't fall into this region, because this is a region of uncertainty. So if the data points were to end up in this region, we wouldn't really be sure about the classification. When I performed these tests, it has resulted in this diagram. So we can see that we have one data point in the region which signifies a supernova. Further, we have 3 data points in the region which marks an AGN, active galactic nucleus. We do have 4 data points in the uncertainties region, and these lines that you can see sticking out of the points are the propagated error bars. So, what exactly does this mean? Are we able to draw any conclusions on the nature of the object, or is it still unknown? Well, even though we have one data point in the supernova region, and the object first was classified as a supernova, it is not that likely that the object is a supernova. And even though we have 3 data points in the AGN region, we can't say for sure that it is an AGN either, because in order for us to be able to draw a definite conclusion, we would need to have consistent data points in one region. And we don't have this, since we have a lot of scattered points and some in the uncertainties region. In order to draw a more definite conclusion on the nature of this object, further studies could aim to use different classification schemes, since the BPT diagram has shown to not be effective in this case. Further studies could also aim to improve the quality of the data, and this can be done by improving the quality of the spectra. If you direct your attention towards this blue line at the top, you will see that it's very pointy and it has a very bad resolution. If you instead look at this spectral line, you can see that it's a lot better. We have a lot more data points. This improves both the error bars, it makes them smaller, and it also makes a better position it also gives the data points a better position in the BPT diagram. So, what conclusions can be drawn from this? We know that the object probably isn't a supernova. We know that it could be an AGN. But we also know that we're still not sure. However, we know that further studies could aim to look at another classification scheme in order to gain a more adequate conclusion. But I want to finish with discussing why we should study this. Why is astronomical classification important in the first place? Well, when we classify astronomical objects, we look at the physical properties and then put them into groups with other objects of similar characteristics. Since we look at the physical properties, that means that when we're uncertain about the classification, we're in fact uncertain about the nature of the object itself. So therefore, studying astronomical objects could help expand the field of astrophysics. This study would not have been possible without Race for Excellence and their partners Åhléns-stiftelsen and Beijer-stiftelsen. I also want to direct a big thank you towards the organizers of Race 2024 and the X-Rays who have helped me during the writing process. Thank you for listening.
Thank you so much, Sofia. Are there any questions from the audience?
Let's start over there.
Picture in the beginning,
Yes? No, that's just a picture. We take frequent scannings of the sky and see if there's any difference in magnitude. So this just shows the object. Any other questions? Yes?
If the object is something else, do you know that it could be either this or that, or are there like 50 different things that it might be? Or?
I would say more along the lines of 50 different things. I mean, it's definitely challenging considering we look at the spectral lines, but the many elements are present in many objects, so we are quite uncertain. Yes?
Out of curiosity, what kind of supernova did they classify?
It's a type 2 supernova that it was classified as initially. And a type supernova means that it has a presence of hydrogen lines. Yes?
Isn't this like research when it's most exciting, because you might have discovered an object that is until now unknown?
Yes, exactly. This is the way that new things are discovered, by looking at objects that we're unsure of, trying to classify them. So perhaps my mentor will continue studying this, and who knows? It could be something that no one's ever observed before.
Do you know what the next steps are? Like, how do we move on from this?
Yes, I do know some parts of further studies. For example, one alternative could be to look at the ratio between the hydrogen alpha over the hydrogen beta line. This could also tell us something about, since, there are different ratios in supernovas and active galactic nucleuses and other objects, so they have similar ratios. Yes, any more questions?
Okay, thank you so much, Sofia.
Thank you.
It's now time for a break again, and we'll be back with more presentation at 3:15, so make sure you're back on time. Thank you for listening.
Det är ju inte brist på det i alla fall.
Det kan vara ett ögonblick där Henrietta är tyst. Det finns bara lokalkommunikationen. Jag svarar också på min egen mobiltelefon. Men jag kan påstå att jag bara drar ut kabeln och också mikrofon. Som kan vara lite sämre. Men de verkar tycka det är så.
Vi kan kika på det. Sen om vi kan klippa ihop någonting.
Det går att rädda det.
Ja.
Så du? Jag tänkte att dörren öppnar alla grejer.
Ja, men...
Det är bättre.
Han körde Deutsche Demokratische Republik. But you have to rewrite a lot. You cannot just take the text and make it a bit short because you have to remove
Ja, det är bra. Men 94 konsumerar 48 timmar varje examen.
I mentioned the in the photograph, and then when I proved it in one final time, I saw that and I changed it. What if I hadn't like noticed that?
I didn't see it. Okay.
But is it? Yeah, we have fun activity tomorrow, meaning that we'll clean all the facility.
But we see that you have time to. As long as you have fun, then it's.
Yeah, I really fun.
There's a phone there. I have a little drama because last year I lost my wallet here. In the race presentation.
You have your wallet now?
So I lost it, and then I went home. So I went home and then I realized I came back to the museum. They were like, "Oh yeah, now we close," but the cleaning person didn't see anything, so it's not here. But call tomorrow. Okay, I called tomorrow and no, I didn't find anything. I'm sorry. I was saying to my friends, they don't want to because this was the last thing they did for the summer. I mean, in this case. So I said, "Oh, they closed down the place and then sorry." But I did the whole process. Reported to the police, took the new cars, new driver license, everything. And then in September, when they reopened the museum, I got a call from the museum. "Hello, we have found the wallet." And I'm like, I really want it now. I really want it now because I was like, oh. So I came and took the wallet.
That's even like almost more work you have to do because you have to discard the cards because they are not useful, but it has your information on them.
Yeah. So I was like, why? I was with her when I got the call because she was visiting us. And I was like, wait, I have everything now. And then I was actually thinking immediately here forever. But so what's the plan? To see we cannot stay, I mean, at least I cannot stay for the rules.
Yeah, I think the presentations are going on until like 5.
Yeah.
And then there's a fancy dinner. Where? But it's dinner at least. And then we have a test when we get home at 11 o'clock. And I think it's a test about Hamlet. And I don't remember anything about the book. I will do that last minute.
Yeah, but I mean, you know, after this you just want to sleep.
Yeah, exactly. I'm sleep deprived. Yeah. It was one time I was just writing on my report, and then all of a sudden it was 6:30. I was like, oh shit, I need to sleep.
Yeah, of course. Yeah. But I mean, now enjoy that you really delivered. Super good. The report was. We sent it. I sent it to them. They were like, and then during the presentation, we were saying
the
like.
report was very close at my final really.
Yeah.
But we'll do about that, because I was thinking about doing, because I did some of the things you mentioned that I had the time to do, but the major ones I haven't fixed. Do you want me to fix it and then send it to you, and also send it to Race, or is the one that I already submitted good enough for?
The one for Race is good.
Okay.
From now, what we're focusing is on improving it so we can do the publication later. And then you can send it in the OneDrive, the updated one. And then also the Word document, because it's easier for us to copy things from there to the.
Are you just not touched?
Or and then we will figure out how to do it.
I don't even know how to send a touch file, but
I guess it
how to.
We will see what we do. Something, I guess, otherwise and then maybe individual figures separate.
Yeah, I did the chemical figure by myself in my touch. It was that was difficult. It took 1 hour because I accidentally put a dot into the code, and then I didn't figure out what the trouble was, and then I removed the dot and then it worked.
We use Tekniska which is easier for idiots. Like you put a line, another line, another line, and then you get the chemical. So now you know more than us for sure. Yeah, but just put the figures in the OneDrive, and then if you can put the latex, put it there, or we will do something with it. But not now, because we don't have time now. And now you just relax and remember us.
Yeah.
But you have something there that probably you would use to remember. Let's see.
Maybe. No. This is my questions. The questions I got were also more difficult.
They were.
The other people
I'm
got
telling you,
hard.
not those.
Yeah.
They were conference level. Absolutely.
Oh, so there are two presentations now before us. Oh, did your mama? It was his mom asking the top questions.
Okay, now you know.
Is she about really tough?
That's why she asked about the microbiome. She thought it was more biology.
Is it chemistry?
All the microbial tests that we do like a biology lab. So it's a collaboration. I send the samples, she does the technical stuff. We do have a security
But then how does it go?
because we have to pass through a call, a lot of security measurements, so then it's better for you to collaborate with someone who does all the stuff. So we send it to them.
She said it, so we did.
And then they do it first.
So the first rows are.
It's also
Does
the
she
way.
write a letter for this?
Yeah.
What? Okay, so she gets something out of it as well.
Yeah, she gets the offer. So she and her colleague, they're in the so this is maybe the same as when you buy shares in a company. The companies that are out, you have different names of shares. Invest time. We do it with them because we don't have the expertise. So and then the data, we cannot really interpret anything, only shooting in the sky. But they can properly do an analysis.
That was the only chemistry project this year.
Yeah, I think it was super good. I mean, it's for sure more understandable than super
You're even more like det var den första tre, va? Ja.
sätta det på de främsta.
Men vi kanske inte borde sitta här.
Nej, jag tänker att vi inte behöver det.
Har ni öppnat?
Jag var ju bättre med komposition för någonting och sen laddade i sig.
Ja, men vilka också.
Ja, precis. Ja, har det varit mycket innan jag kom?
Alltså menar du mycket idag eller mycket generellt?
Mycket idag.
Ja, så vi har suttit här sedan klockan 10.
Ja, ni har suttit
presenterat.
Jaha. Så du har hört alla andra presentera?
Ja, precis. Jo, vi alla hör varandra.
Ja.
Så att jag var ju den sista av alla.
Ja, så du har fått sitta hela dagen?
Ja, så att det var lite roligt att liksom sitta och vara nervös.
Ja, jo, jag förstår det. Det var ju synd. Men
ja, men det är inte hela världen. Någon måste vara sist.
Ja. Det var inte den här presentationen var supernovad eller inte. Det var väldigt intressant. Ja, det är mycket att förstå för eleverna.
Ja, men det är bra. Det är meningen.
Ja, jag förstår. Ja, men det kan vara så lekman när man inte alls är inne i forskningen. Känner du till någon som presenterar?
Ja, alltså jag känner ju henne. Hon har ju gått på liksom det här forskningsläget som också gått på. Precis. Så jag känner ju alla som presenterar.
Du känner alla. Vad står RACE för?
Research Academy for Young Scientists.
Jaha, research med program.
Så det är ett program.
Ja, det står ju under vad det är, men liksom vad det står för. Det är engelska uttryck. Jag ringde till mamma sen när jag hade pratat med dig och
pappa lät också såhär en dag. Det var väldigt snabbt att säga att nu kommer jag.
Det var kul.
Ja, det är varmt ute idag eller?
Ja, det är varmt för mig. Alltså jag tror att så att är det 23-24 grader och jag måste vara ute mycket så känner jag.
Just det, mormor också. Det här är Olle som är släkt med oss.
Jaha.
Han heter Lapidus i efternamn.
Ja, men det var kul.
Ja, hej.
Låt oss här sitta. Hej. Och då ska vi se. Är det som till?
Son till John Lapidus.
Ja, till John.
Ja,
som det
så är det Leif
som är Leif, ja. Och Leif är min syster.
Ja.
Men hans pappa bägge och min far också. Ja. Vad så livet. Vad kul att vi får det dyka upp för att kunna träffa honom.
Ja, det var väldigt spännande att lista ut det här.
Jag misstänkte ju, jag visste vad du hade efternamn. Men jag hade ingen aning om att det fanns Lapidus i Göteborg.
Nej, det visste inte det. Precis. Det var antagligen mycket ungdom, men vi hade en
Jag tror det.
Har du varit i Eleverna?
Ja, alltså han är också projektledare.
Ja, förlåt.
Nu är jag projektledare. Det tycker jag har deltagit.
Ja, men det är spännande som man får tillfälle tycker jag. Jag kom så att jag hörde på den här presentationen.
Ja, men vi har försökt tanka i dem att det ska gå till så att jag ska testa på det. Det kom som kommer till
Undrar om folk nu kan få fota upp. Familjen och reser hela landet liksom. Ja, han kommer nog bli stolt över vad som helst.
Ja, exakt.
Har du syskon och så här också?
Ja.
Nej.
Jag tror det. Alla använder honom. Och sen får man inte precis
men samtidigt, jag menar, du måste stanna någonting och transportera en laddning avstånd. För det är ju ändå en förflyttning av en fysisk partikel, inte genom tillståndet. Tack så mycket. Jo, de får det. Det är ju bara för att man inte upplever den skalan, för att det är på mindre än i praktiken så är ju en elektron i en vakuum när den är runt sin atom. Så därmed finns det inget som skulle bromsa den. Men och liksom superledarskap, det måste ju, det är ju by definition ett elektriskt arbete att tillföra en elektron från ditt laddningsöverskott till kabeln och sen på andra sidan tillföra en elektron till underskottet från kabeln. Det måste ju kräva arbete.
Den sektionen var intresserad av de andra bitarna i samhället.
Det ska inte funka. Alltså, obviously gör det. Hela grejen är ju att allting blir värme egentligen. Och här har vi något som bara inte blir värme. Det är skitsus.
Det är skitsus. Det var därför jag hade en super låg maskin.
Jag skulle säga att jag var den bästa kombo.
Jag fattar absolut inte vad du menade med någon man hade gått.
Menar du? Det funkar ändå rätt så bra. Ja, bra jobbat. Det är tur att ha en i...
Ja,
Det gör lite mer el.
Om det förändras... Nej, hur säger man det? Det är
Okay, welcome back from the break, and I assume we have some new people in the audience, so security for like the third time. You have emergency exits on both sides of the stage. In case of emergency, the assembly point is outside the main entrance of the Ethnographic Museum, which is just the opposite side of the street from the main entrance of the Science and Technology Museum. So, for now we have our final 3 presentations. And first up is Isak Karlsson and Muammar Al-Jaburi. Isak, who does everything from singing choirs to build his own rockets, studies at Katedralskolan in Uppsala. Muammar, who studies at Presiditas Malmö, also has broad interests from competing in table tennis to his main interest, medicine. They're now going to present their project about using machine learning to predict health. Welcome up, Isak and Muammar.
So, what is it that makes us us? Is it our personality? Is it maybe our hormones? Or is it gut microbiome? The gut microbiome is a collection of symbiotic bacteria and a microbiome that live in symbiotic relationships. And we know that there's numerous cells and a million of different microorganisms that live in our gut and that can be studied.
Yeah, and recently this gut microbiome has gained a lot of attention in the medical research, as we found out that this gut microbiome can impact a lot of other functions in the body other than like the digestive system and such. So it's really interesting, and we can maybe use this for like new treatments and improve general health. More specifically, I will look at the gut microbiome's connection to colorectal cancer, which is intestinal cancer. So apparently when there is a disturbance in the balance of the gut microbiomes, there can occur dysbiosis, which in turn can lead to chronic inflammation and hinder some functionalities of the cells, and ultimately lead to cancer. And in this case, colorectal cancer, which is one of the deadliest cancers in the world.
And did you also know that the gut microbiome plays an important role in preserving normal brain function? This shows new possibilities for novel treatments of Alzheimer's disease, which is what I'll be studying. And this is a concept that is known as the gut-brain axis. And what that is a bidirectional communication between the enteric nervous system and the central nervous system. And in the past 2 weeks, me and Isaac, we have worked together in the Karolinska Institute to determine and try to answer this question of the relationship between the gut microbiota and how we can analyze it. And we'll check the relationship between gut microbiota and intestinal cancer and Alzheimer's disease.
Yeah, so how do we approach this aim of study or problem? Well, any sort of analysis would require some data, and fortunately for us, we didn't have to acquire this one on our own, but our mentor, Nicole, found it for us online, and it looks something like this. It has like 800 columns, which consists mostly of bacteria, or the concentration of bacteria in the gut, and we have like 120 patients. It differs a little bit between the studies, but that's mostly true. And we have 6 or 4 meta columns about age and sex and BMI. This is a lot of data, of course. 120 times 800. You can do the math on your own. But I wouldn't want to sit down and like find some sort of correlation on the paper. So we'll need another approach.
Well, I don't know, Isaac, if you have heard about this new tool that is called, and pretty modern, machine learning.
Could you explain further?
Yeah, of course. So to illustrate how machine learning works, we can use a toddler. And you know that a toddler and a machine learning, they have striking similarities. First of all, they both begin with zero information and gather information from the environment. And that is when we employ the toddler training program. What it does is we, first of all, put in information in the data set, we train the toddler, and then we evaluate how good the toddler is at differentiating between different groups in the information. Now a loop has been created, and until the toddler is knowledgeable, that is when we deploy it into the real world and evaluate how good it performs.
Yeah.
And we can also see if we want to teach a toddler what a circle is, we show it circular shaped objects. That is, with different sizes and varying colors. And this will, the toddler will then recognize a pattern of what is a circle. And we can also see that we have to remember that the toddler doesn't know what a circle is, or even what shapes are. And training models seems to be the same. And if we now, let's say, gather enough data about toddlers, or gather enough data about microbiome data and the outcome of a disease, we can train the model to predict and see patterns, and then differentiate between a sick patient and a healthy patient using this pattern. And it's also good to show the circles and non-circles, or introduce the concept of using or using non-circles. That is to make the model not biased. Yeah, and we can see here that our metadata or our data is balanced. So that is good.
So we won't need correct for that. But how do we then know that when we train our model or our toddler, that it performs as it should? We'll need to test it or examine it. And I'll need some help with the math now.
Yeah, of course.
Because we'll take our data and then we'll split it into two sets, the training and the testing. Testing you'll give to a friend or put in your back pocket.
Thank you.
For further use. As for the remaining training data,
yeah,
split it into 5 more parts, because we use a fancy technique called cross-validation, which is when you reuse the training data for both validation and testing. So you take one of these 4 folds, it's called, validate, repeat 5 times until all of the data has been used, and then you take the average and calculate the score. How is this score calculated?
Well, yeah, what we can deploy is a metric called confusion matrix. When using a confusion matrix, don't look at the name, because it isn't that confusing, to be honest. I promise I'll explain it pretty intuitively. And when looking at the matrix to the right, we can see that there is a diagonal with darker gradient. This indicates that the model, the correctly predicted values, and the remaining 2 boxes with a lighter gradient, that indicates the wrong predicted values. And what we want our model is, it should look like this. When looking at this model, we know that it performs worse.
And unfortunately, this isn't quite enough for a scalar value performance of a model. So we'll need to develop it a bit further into the AUC value. So you get that by plotting the TPR and the FPR, which is the true positive rate and the false positive rate. Basically, it's the amount of sick patients that the model correctly predicted as sick against the amount of healthy patients that the model incorrectly predicted as sick. You'll get the ROC curve if you do this at different thresholds for the model, and under the ROC curve is the appropriately named AUC, area under curve. You'll want to maximize this area under curve, thereby you maximize the amount of correct predictions, and that is our scalar value and the most the mostly used value when evaluating these models.
Yeah, exactly, and we know now how to evaluate the model, but can we enhance the model even further? That is when we deploy the ultimate toddler training program. And what that includes is we first of all test different machine learning algorithms and decide which one is the most optimal. And also we can process the data and see how that maybe enhances the model's performance. And
now I'll finally get to use my favorite metric, area under curve, to determine the performance of these 3 models. They were the gradient booster machine, random forest, and simple vector machine. You won't need to remember those. But the gradient boost machine turned out the best in this case and is the model we're going to use.
Yes, and now when we look at data pre-processing, we can see that if we do a transformation, a center-log ratio transformation to the data, we can see that this enhances or increases the contrast between the relatively low abundance of microbiome. And here we can see that if we now, let's say, let's suppose the crowd is now a machine learning model, which one would we want to use? Of course, this one. And we can see that the CLR, what it does to the model is that it hinders it from being biased towards one class. And when looking at the arc value for the center log ratio, before and after, we can see that it increased the arc value with 0.06, meaning that the model is now enhanced.
Then we have one final way to maybe pre-process the data and make it a bit easier for the model. That is choosing which columns to use for feature selection. So one thing you can do is plot the different models. One dot is one model, and once again the AUC score and how many columns were used in the data. And here you can see that the sweet spot lies around 400 columns. Too few and you won't get enough information. Too many and that's just noise. So we're going to use like 400 columns.
Yeah.
Then, when we have done all of these steps, we have chosen the model, we have done all the pre-processing, we'll want to finalize our model. That is, train it on all of our data and all of our tunings to get one final cool AUC score. And you're probably waiting for like the 0.99 right now, but I would be probably concerned if we got 0.99 because that is probably a result from overfitting, which is bad. A high ISQ score is not always good. Because overfitting is when the model gets a bit too comfortable with the data and learns the ins and outs and like makes exceptions for randomized data, which is bad.
Yeah, and when the model is underfitting, we know that it simply performs worse. So what we want is an appropriate fitting model, and that is because of when looking or testing the models on unseen data, new unseen data, we can see that it outperforms both the overfitting and underfitting of the model. We can also see that on the overfitting of the model, it has a structure that is closely aligned with the previous data set. So when it's introduced with new information, it performs worse.
Which leads us to one.
And we can also see that if we use the testing set that we have, the testing set, and try to see how it works with the final model, we see that it yields a arc value of 0.67. This is good, however, it's worse than the training set, and this is of course because of overfitting. So to mitigate the effects of overfitting, we can use cross-validation.
Yeah. Now, when we're done with our model, we can do one of my favorite things, that is analyzing the finished product to notice patterns and like more useful knowledge. We could do a feature importance test, that is looking at all the features or columns the model used and rank them in according to how useful they are for predicting the label of the data. In this case, which is my colorectal cancer, 2 bacteria and 1 gene test were the most important. And this is really interesting because then you could like look at this Fusobacterium nuclearum and see what does it do, and could you maybe develop a treatment or use it to improve, do some therapy and lower the death rate of colorectal cancer.
Yeah, we can look at if we can applicate our model on clinical practices. And by using a microbiota-based model, we can use it as a non-invasive technique to determine if a person is sick or healthy. I know that in Alzheimer's, there's an accurate way to diagnose, which is using lumbar puncture, and this can in the future replace it. And our microbiota-based model, it also uses fewer parameters, and this means that in the future, it can be much more cost-effective and accessible. And when I tried to look at how good my model was, the final model, I came to some surprising results. My model yielded an accuracy of 77 in diagnosis of Alzheimer's, while a study that was conducted at the University of Washington saw that an average neurologist yielded a 71% accuracy in diagnosis, which, hypothetically speaking, means that my model outperforms a neurologist. But is this all the truth? Well, not really. If we look at the final model and evaluate it using the testing set, we can see that it had a 0.67 OC value. That is 67% accuracy in diagnosis, which is worse than the neurologist or an average neurologist that we saw in the previous study. The same holds true for 95% confidence interval if we look at that in our a model that was trained on a training set. If we look at the lower boundary, it scores a 61% accuracy in diagnosis. That means that we can't use our model yet. We need to see further advancements before we can see clinical implementations.
So, what further developments? We believe people should use bigger data. Easy to say, hard to achieve, but that was one of the limitations when we performed our analysis. It was hard to balance the amount of data used for the testing set, because that you wouldn't have now for the training set, which would cause underfitting and overfitting, you get it. And we would also like to see time-based or longitudinal study, that is including different timestamps for the data collection and looking at the development or difference in microgut biome, because that would perhaps give further knowledge about what causes what when dealing with these bacteria and the colorectal cancer or Alzheimer's. We could also standardize the collection and analysis of the extraction of stool samples, because that would help in adding different data sets together and improving the general model, which could, of course, be used in both science and in the clinical practices where accuracy is really important.
Yeah, and if, in conclusion, the study implemented machine learning models to determine Alzheimer's disease and colorectal cancer using microbiota data. And we also looked at the clinical applications of the final model. Afterwards, before that, we saw how data processing can enhance the model. And if it is so that you have forgotten now everything that we have told in this presentation, we want you to remember one thing and one thing only, and that is you can use a toddler as an analogy for machine learning models. They are striking resemblance. Now we want to thank and extend our gratitude to our wonderful mentor, Dr. Nicole Wagner.
We would also, of course, like to thank Europaskolinsträngnäs for housing us this time.
We also want to thank Tagges Fonds Stiftelse för undervisning och forskning.
And Magnus Bergvalls Stiftelsen.
As well as Beijer Stiftelsen. And we also want to thank Race for Excellence and all of the wonderful students, and also the Race 2024 organizers, and also X-Rays. Thank you for listening.
Thank you so much, Isaac and Ronald. So, are there any questions from the audience?
Yeah, introduce.
Yeah, quick question. If you could go back to the AC curve. Or more specifically, the ones that you used. No, this one first. Because you've got false positive and true positive rates against each other. How would have you also done studied your argument for false negative and true negative rates?
As this is a binary classification model, those complement each other and isn't interesting.
Yeah, there should be right. No, maybe not.
They are literally the inverse of each other.
Yeah, maybe are. I mean, I thought about this.
Yeah.
When you did feature selection, how do you decide which columns?
Great question. We use the same feature importance test as I used when telling. So what you do is, this is a tree class-based model, and you look at each node and go through all the threshold values for the model, and then you decide based on how much of an impact it has on the decision, because this is binary classification as well.
Yes. Do you want to continue maybe, or?
We could continue, but I don't think that'll...
Yes, Danny, question.
Just wondering, what kind of version have you done here? Because it seems like the data is kind of jumbled out.
The fifth line, you mean? Yeah. Some random, that's just for illustration.
We are just using a smooth curve. So when we plotted this and in programming, we did a smooth curve to see if we can see any good.
Do you know the accuracy of correlation of that?
So we have another graph that shows the accuracy, and we can see here that this point is the highest, or yields the highest as when we are looking at the number of columns used.
We have not used the values from that specific fit line in our model, so it's only for presentation.
In medicine, do we prefer underfitting or overfitting?
Underfitting, because overfitting is completely useless outside of your data set.
Exactly, and overfitting is like a person or a student learns and memorizes practice problems, and then when the professor brings the test, they score badly. Why? Because the test doesn't have the same questions as the student had memorized. So that's how overfitting works.
Yeah. Okay, so...
No, not true.
Yeah. So you're using stochastic or deterministic models. Will it always give the same result based on the same input?
We are using a seed, so that would be deterministic.
Yeah. Yes, Jacob?
Yeah, Mohammed, you were very close, your model was very close to outperforming a neurologist. How much time do you think there is left until, or how much time would you need for your model to outperform them in reality?
Very good question. So what we are doing is in further studies, we can look at more using bigger data sets and see how we can use different metadata. I know that in the Alzheimer's disease, we can look at the ApoE4 gene, which is a risk-determining factor for Alzheimer's. And if you use it in the model, it yields a pretty high value.
I would start looking at the job market if I were them.
Yeah.
What can we eat to strengthen our gut biome?
Well, generally a diverse microbiome is good. It's like maybe those weird Provica juices and that strengthen diversity and rebalance of your microbiome if it were to happen something that could disbalance it.
So I think also a way that we can enhance our diet is eating a lot of fibers that we can find in bread and in many other whole foods. Alan?
Yeah, so the neurologist, the test that was done by Washington University,
Yeah.
was that neurologist doing a classical test, or was it neurologist looking at microbiome data?
So what the neurologist did was a classical test, or what we call the classical test, which is using a memory test or an MMSE. What they also did is they interviewed relatives to the Alzheimer's disease patients. And with these two, plus using, this is not stated in the study, but many other ways is using, let's say, the lumbar puncture, which we mentioned in clinical applications. And with this, they can determine if a patient has Alzheimer's or not.
So the lumbar puncture is not very accurate in
It isn't stated in the study, so we don't know. However, they stated specifically that they looked at MMSE, which is a memory test that we use to determine if a person has Alzheimer's or not, and interviewed relatives, which is the classical way of diagnosing.
Last question.
Yeah, I think we're when you speak of true and false positives, you mean positive classifications as a whole, and not just true classification saying, okay, we think that this person has Alzheimer's.
Could you further?
I mean, when you speak of true positive rate and false positive rate in the seeker once again, are you speaking of all classifications that you tried for both positive and negative diagnoses, or just positive?
In the AUC curve, or the ROC curve it's called, the true positive rate is the proportion of all positive patients, that is the disease or the sick patients, that the model has labeled as sick. Does that answer your question?
Yeah, but then it should not be true or false negative rates, because you can have different accuracies for...
I can show you the negative later.
Yeah. So we want to thank the crowd for the patience.
Okay, thank you for this lovely debate about true positives. And also, thank you, Isaac and Muava, for your presentation.
Does anybody want the testing set?
Okay, next up, Hanna André. Hanna studies at Presentation Malmö and has previously competed in both chemistry and biology. But her main interests are actually maths and physics, partially due to her passion for Formula One. She is now going to present her project about wind tunnels. Welcome, Hanna.
Thank you. So, in my project, I was doing the design and construction of boundary layer rigs for measuring boundary layers in subsonic wind tunnels. So, when I heard about this project, my third thought went to Formula One, of course. Because what is Formula One if not the pinnacle of motorsports? But why is it the pinnacle of motorsports? A big part of it is the construction and testing that the cars go through. Some of that testing happens in a wind tunnel. A wind tunnel can look something like this. This specifically is the KTH L2000 wind tunnel, which is where I was doing my tests. And subsonic wind tunnels are lower speed wind tunnels, usually at Mach 0.3. So, when a wind tunnel works by, when you put an object, you blow lots of air at different velocities in it. And then you take the data from that and analyze it to develop the vehicle, plane, or whatever it is you're testing. And when a fluid is moving over an object or a surface, something called boundary layers will appear. A boundary layer is what's happening when molecules move over a surface or an object, and they will get stuck in the roughness of that object. So the velocity the molecules will have at the surface of the object will be 0. Then the velocity will gradually become higher until it reaches the free stream velocity. And the boundary layer is the spacing between the surface of the object and the free stream velocity. There are 2 types of boundary layers that are often referred to, but there really are something in here between. They're not quite yet turbulent and not quite yet laminar. What's interesting for us are the turbulent boundary layers, because these boundary layers will appear on any surface that you blow air at or a fluid, and therefore these will appear in the wind tunnel when testing. This can sometimes be a good thing. Cars, for example, are driving on a road, and there will appear boundary layers on the road as well. However, when you're testing something like an airplane, they're most of the time in the air, so these boundary layers will not be relevant. When testing an airplane, you will therefore have to place it above the boundary layer. And to do that, you have to know how thick the boundary layers is. This can be done by boundary layer rigs. So these are 2 of the boundary layers that I built. And what a boundary layer rigs is that they are structured, as you can see here, with metal tubes inside of them. They are then connected to a pressure scanner that measures the total pressure. But what we're interested in is the dynamic pressure. The dynamic pressure is calculated by Bernoulli's equation, as is seen here, which is the total pressure minus the static pressure. The static pressure is what we often refer to as atmospheric pressure. It doesn't change. And with the dynamic pressure, you get the velocity of the equation. And by looking at when the velocity is the same as the free-stream velocity, which is the wind speed that's entered in the wind tunnel, you know when the boundary layer has ended. So what I did was that I designed and constructed 5 of these rakes, all with different tube diameters, to see if there was one clear winner of tube diameters that measured the boundary layers more correct. So I started with designing these rakes, and then I had to look at all sorts of things. One of those things was the height of the boundary layer and the placement of the tubes. The height of the boundary layer had to be taller than the actual boundary layer, the boundary layer rake I meant before, which was estimated using imperial equations. And then the placement of these tubes, which are the holes here, would have to be closer at the bottom here, as you can see, since the boundary layer is thinner at the beginning of the tunnel than it is at the end of the tunnel. So this was a model of one of the rakes that I did in the CAD program. And after that, it was time for the construction of the rakes. This was done by 3D printing them, and I started printing them in 2 halves that were then glued together. Then the tubes were added inside the rake, and there were connected plastic tubes to those tubes that were then connected to even smaller plastic tubes that were named 1 through 16, because that's the number of ports available in the pressure scanner. And then these were connected with tacky tape, and yes, this looks a bit messy, and it certainly was. And then they're connected to this pressure scanner, which then again measures the total pressure, but inputs in the data set the dynamic pressure. So then we go on to the first test, which was a verification test. The boundary layer rakes were placed on a tall platform, which was taller than the calculated height of the boundary layer. Then we tried different velocities at the wind speed to see if the pressure was measured correctly. What we wanted to see was if all of the tubes on the rakes measured the same pressure because there was no boundary layer to interfere. This produced a plot like this. This is a very good result since this was tested at 20 meters per second, and then each of these points represent the pressure that a tube measure and then the velocity when we input it in the formula. We also tested at different angles to see if that would make any difference. This was mostly because we wanted to know how exact we should be when placing them in the final test. When these tested had succeeded and all of the rakes measured the pressure correctly, we moved on to the measuring of the boundary layer. We then placed the boundary layer rakes at different distances in the tunnel, as seen here, with the flow coming this way. So we tried it at the beginning of the tunnel, the middle of the tunnel, and at the end of the tunnel to see how the different boundary layers thickness was there. So this is the first one, which was tested at the beginning of the tunnel at a velocity of 20 meters per second. And then each of these points again represent the tube, but then the colors represent the different rakes. There are some outliers, which is simply because the tubes weren't properly connected, so those we can simply ignore. And we see here that pretty much all of the rakes measure the same thing. This implies that it isn't that big of a difference. And if you want to see how thick the boundary layer actually is, it's around here, 40 millimeters, when the velocity is the same as the free-stream velocity. If we move on to the middle of the tunnel, where most tests are conducted, which is therefore more interesting, we get this graph. This was also at 20 meters per second, And this looks a bit different. We still have the same outliers, but as we can see, the 2.5 millimeter rate measured a slightly higher pressure, which resulted in a higher velocity. This might be because of unevenness around the floor at that specific place. It could also be simply because that rake doesn't measure the pressure as well as the others, which signifies that that tube diameter maybe isn't ideal. And finally, we measured boundary layer thickness at the end of the tunnel, which gave this graph. As we can see here, the 2 millimeter tubes showed a slightly lower value, but the other ones showed pretty much the same thing. So what we can conclude from here is that it doesn't matter a whole lot which the tube diameter we use. We did see on these graphs that the one using the 2 millimeter and the 2.5 millimeter tubes did have some outlying measurements. However, it wasn't a lot. Another important factor when measuring is that the boundary layer is at its thinnest in the beginning of the tunnel, and then you would ideally have more measurement points, which you would get by having a smaller tube diameter. That would be pointing to the 3 millimeter tubes being a better choice. But the 4 millimeter and maybe not the 5 millimeter would measure the boundary layer correctly. So, if someone ever talks about you to Formula 1, you can start showing your skills that you learned in this presentation. And I just wanted to thank my mentor, Juli, for mentoring me on this project, and I want to thank Race for Excellence and the organizing group, and finally the partners Tagesfons Stiftelse för undervisning och forskning och Olle Engqvist Stiftelse. Thank you.
Thank you so much, Hannah. Are there any questions from the audience?
It's simply because they all measure the same. As you can see here, there's some slight blue, some slight green. This just shows that it doesn't really make a difference whether it is 0, 10, or a -10 angle of attack. Simon?
Looking at the other graphs, there was always like one outlier. If you can, yeah, like there, you see the purple ones. Like, what's the explanation for that?
Well, these outliers, as you saw before here, this is quite difficult to all get correctly. There are 80 tubes that need to be completely airtight at like 3 connections. So we did our best to make everything airtight, but as you can see here, there were, some outliers, and these were all the 5 millimeter tubes, and it was simply because they were larger and had to fit inside a smaller tube, which made it more difficult.
Were you measuring it at a specific wind speed?
Yes, I did measure at tons of different wind speeds. More than these here, I just picked these plots because I thought they showed the results best, but it was all from 10 to 30 meters per second.
Did the height of the boundary layer depend on the wind speed?
Yes, it does depend on the wind speed.
Were you allowed to be in the wind tunnel when there was wind coming at you?
Yeah.
Does the entanglement and how the tubes were bent impact the measured pressure at all, or was that something you took into account?
If the tubes were bent so that the air couldn't pass through, that would affect, but...
If you had a straight tube and a tube that all tangled up, would that impact the measured pressure? You know?
I'm not completely sure, but I do know that the thing that we used now gave the correct velocity, so it didn't impact a whole lot.
But it would have been ideal to have it more strict and easy, but that wasn't possible.
Yeah, one final thing. What does the distance of 0.00 meters mean? Like the calculated velocity and the distance of 0 meters.
Yeah, it's simply that we started at the beginning of the floor of the wind tunnel. So the floor of the wind tunnel is 4.45 meters. And then we started like here at the very beginning, where it should be the thinnest.
You said that the velocity of the wind tunnel at KTH is about 0.3 Mach.
Well, that's usually how subsonic wind tunnels is classified. I think the maximum velocity at the KTH wind tunnel is about 60 meters per second.
I was just going to ask if you tested up to that velocity.
No, we didn't. It was up to 30 meters per second.
Okay, seems like there's no more questions. Thank you, Hannah.
Thank you.
Okay, we've reached our final presentation. Last but not least, Nadia Kuritsin and Alan Ismail. Nadia, who has previously done research in astrophysics, studies at Campus Victor Rydberg here in Stockholm. Alan, who studies at Katedralskolan in Växjö, has completed extensively both in linguistics and in experimental science. Their project is about gravitational waves. Welcome up, Nadia and Alan.
Hello there, audience. My name is Alan.
And my name is Nadia.
And today we've been honored with holding the final presentation for RACE 2024. We all know that we might be a bit tired from all presentations today, so our goal today is to not bore you too much. And with that being said, let's get into the utilization of the inverse Gertrude-Stein effect for detection of high-frequency gravitational waves.
So, what is a gravitational wave? A gravitational wave is a ripple in space-time, which means that when a gravitational wave is traveling through the universe at a speed of light, it squeezes and stretches space-time as well as the objects within it. But how are these gravitational waves generated? Well, so the strong gravitational waves, which are the ones that we can possibly detect from Earth, are generated by extreme cosmic events, such as the merging of two black holes or neutron stars.
So to demonstrate how a gravitational wave works, Nadia and I will now hold a play for you guys. I will be representing
an object?
Yes, an object, and Nadia will be representing the gravitational wave of which the object passes through. So let's begin. And that is approximately how a gravitational wave works.
So what types of gravitational waves can we detect today? In 2015, the first gravitational wave was detected by the LIGO-Virgo network, which detects gravitational waves with the most accuracy in the 1 Hz to about 100 Hz frequency band. In addition, pulsar timing arrays have also been utilized to detect gravitational waves, but in the low frequency range, with the most accuracy in the nanohertz region. However, there is no established method or tool for detection of high-frequency gravitational waves. And therefore, Alan and I are conducting this project to investigate a possible method to indirectly detect high-frequency gravitational waves.
So, now you might think, why do we even care about this part of the frequency band? Why do we care about high-frequency gravitational waves? Why do we want to detect them? And to answer that question, Nadia and I first have a secret to admit. Currently, we don't know of any astrophysical objects or astrophysical phenomena that would be able to generate a high-frequency gravitational wave. But that is precisely why we're so interested in them, since such a detection would then indicate physics beyond our current understanding. It could, for instance, indicate different types of cosmic inflation, which is the really, really fast expansion of the universe that happened right after the Big Bang. But it could also indicate exotic astrophysical objects such as boson stars or super teeny whiny tiny black holes called primordial black holes that could be the size of an atom. So, how was all this done? It was done through maths. And when I say maths, I mean a lot of maths. But you, their audience, will be able to understand the entirety of this project without needing to know a single letter of Greek. So let's get into it.
So, at the heart of our project, we find the inverse Gerzenstein effect. And the inverse Gerzenstein effect suggests that when a gravitational wave, denoted by H, interacts with a magnetic field, denoted by B, there is a small chance that this gravitational wave can convert into light. And what's worth noting here is that this light will acquire the same frequency as the gravitational wave it came from.
So, once again, it's time for a play. I will be representing the gravitational wave that passes through the magnetic field, and we will see what happens. So I come here. And as I enter the magnetic field, I become light. And that is approximately how the inverse Gerzenstein effect works. The beautiful thing about the inverse Gerzenstein effect is that even though we're not able to detect the high frequency gravitational waves, we are able to detect the light that comes out of it. It can be detected by normal radio telescopes, or it could be detected simply by the antenna that you have on the top of your roof, if you still have one of those. But now some of you in the audience might think, how do we differentiate from this fancy normal light from all other light? And that is a really good question, and is actually what's difficult about our project. So to get into that, we need to go into a bit of theory about the cosmic microwave background, or CMB for short. When the universe was really young, it was a lot smaller and a lot hotter than it was today. The universe consisted of an electrically charged plasma that would instantly absorb any and all light that is emitted, which means that the entire universe was opaque. But as the universe expanded and temperatures cooled, matter was eventually able to form. And this matter wouldn't absorb light to the same extent that plasma does. So for the first time in the history of our universe, light was able to travel freely. And this first light that was released 13.5 billion years ago is what we know today as the cosmic microwave background. But the cosmic microwave background released 13.5 billion years ago was quite a long time ago. Like a really long time ago, even before the dinosaurs existed, if you would believe it. So during this time, the cosmic microwave background has become contaminated. It has been contaminated from other sources of light. But as the saying goes, one man's trash is another man's treasure. And in our case, this contamination, or this foreground of the CMB, is actually what we're so interested in, since one source of contamination in the foreground is actually from the inverse Gerzenstein effect.
So how do we then isolate the photons induced by the inverse Gerzenstein effect from the other photons on the CMB's foreground? Well, we're doing this by using data from radio telescopes, as well as mock data from telescopes that are being built right now or proposed to be built in the future. And so these telescopes are accounting for sources of the foreground, these contaminations or perturbations, as they also can be named. And by subtracting these perturbations from the foreground as a whole, we can isolate the photons induced by the inverse Gerzenstein effect. So we then assume that after subtracting all these other sources of foregrounds, we are left with only the photons that are induced from the inverse Gerzenstein effect.
So now some of you in the audience might think, how can you make this bold assumption that we're able to isolate all light that is from the inverse Gerzenstein effect? And that is a really valid question that we will once again answer with maths. Through maths, we're able to backtrack from the amount of light that we say is from the inverse Gerzenstein effect to knowing how much energy or how many gravitational waves there must have been originally to create that light. And that is basically denoted by this, which is the energy density of gravitational waves, denoted as omega GeV. This number relates the energy of gravitational waves to the energy of the entire universe. So if this number would be 0.5, it would mean that half of all energy in the universe is gravitational waves. If this number was 1, it would imply that we wouldn't exist, since everything in the universe is gravitational waves. And if this number was 100, it would imply that the energy in gravitational waves are 100 times the energy in the total universe, which, needless to say, is quite unrealistic.
And there is a limit, or a theoretical limit, even called the BBN limit, for the maximum amount of the universe's energy that gravitational waves can account for. And the limit is the one you can see on the slide. And so if our data would appear below this limit, we could assume that our data fully consists of photons induced by the inverse Gerson effect, which then comes from gravitational waves. However, if our data would appear above the limit, we could not be sure that our data just consists of photons induced by the inverse Gerson effect, but we might have also accidentally included other perturbations.
So it's time for our results. Here we see a plot of the data we use. On the x-axis, we can see different frequencies for the data, and on the y-axis, we can see the energy density of which we talked about. We can also see where it equals 1, meaning that we wouldn't exist. And we also see the BBN limit that Nadia was talking about. And to reiterate, we want to be below the limit. And up there are our data points. Current telescopes are denoted by these solid bars, so you can see the black bars and the green and the yellow. And they all lie in the 10 to the power of 12 to 10 to the power of 14 range, which basically means that we wouldn't exist many times over. And it also means that our data sucks. But there is hope. If we look at this pink triangle here, or not triangle, a rectangle, it's mock data from the SKLO telescope, which is currently being built. And when it is finished, it will be able to give us energy density values of approximately 10 to the power 4, 10 to the power 3, which is a lot better than our current data, but it's quite still far off the BBN limit. We still wouldn't exist. Even more notably, some of you might have noticed this light blue figure over here, and that's mock data from the proposed CMB survey called Voyage 2050. And as we can see, in the terahertz regime, it actually lies below the BBN limit. So, if theoretically speaking, this was built with the proposed specifications, we would be able to detect high-frequency gravitational waves in the terahertz regime. So there is still hope.
This plot shows an expansion of the former plot, and as the former plot which Alan talks about, it compares our data up there in the right corner with mock data in the high frequency range. However, unlike the other plot, it compares with data from telescopes over a larger frequency range, all the way from low frequency range in the nanohertz region, where we see that pulsar timing rays have measured, to normal frequency, where we find the LIGO-Virgo network, and then as well as the high frequency range where we can find our data. And what's interesting to note here, as I mentioned earlier, LIGO-Virgo is they are proven, and it's well known that they are able to detect gravitational waves accurately. And as we see there, the gravitational wave energy density that they observed or calculated is well below the BBN limit, which is where you have to be in order to detect with accuracy, and that just shows how far our results have to go in order to reach the same level of accuracy. So, obviously, our results are not very realistic. The gravitational wave energy in our universe is 10 to the 12 to 10 to the 16 amount of energy in our universe. And the reasons for these results are numerous, but one of them might be that there are a lot of perturbations that we might not have accounted for. As I mentioned earlier about the telescopes, they do account for perturbations, however, they only account for one each. And there are more than 2 sources of the CMB's foreground, and thus our data might not only include photons induced by the inverse Gerdenstein effect, but there might also be other photons in our data from other sources of foreground. Another reason for the results might also be the low probability for the inverse Gerdenstein effect to occur. So let's say that a telescope mistakes a particle for being a photon. Since it is such a small probability for a gravitational wave to convert into a photon, one extra photon results in a lot more gravitational waves. However, further studies should definitely be conducted with more thoroughly studied data, such as data where more perturbations are accounted for, as well as with better telescopes. So our conclusion is once again that the results are not realistic, but that future data and telescopes look promising, such as the Voyage 2050, as Alan mentioned on the first plot, and that we should not neglect the inverse Gerdenstein effect for further studies, but include that one with better data and telescopes instead. So now we just have one last thing to say. We would like to express our greatest appreciation to Race for Excellence, as well as Beijer Stiftelsen and Stiftelsen Oskar och Maria Ekmans Donationsfond for making this project possible.
And Nadia and I also want to give our sincere thanks to our mentor Yutong sitting here in the audience. Without you, this project would have not been possible, and you have made our time here truly fantastic. So thank you. And thank you guys for listening.
Thank you so much, Nadia and Alan. Are there any questions from the audience? Oh, a lot of them.
Let's start on the left, Bunny. Oh, we took that from a study, so we didn't do that ourselves. It's just a well-known limit that has been calculated.
Benjamin?
No, there is no unit. It just relates to the energy of the universe. So 1 equals the energy of the entire universe.
Simon?
What are the perturbations to look at?
So the perturbations that the telescopes that we have used account for is something called the 21 centimeter line and the KSC effect. They are quite intricate to know, but there are also many other perturbations. I mean, we don't really know all of the perturbations either, and that's also what's causing the problem to eliminate them then. But possibly axions, which is a particle that might not even exist, as well as neutrinos and many others.
You can read our paper.
Sorry, you may have said this, but what is the lower bound for what is considered a high-frequency gravitational wave?
Oh, no, we actually didn't mention that, but it's approximately 10 kilohertz or higher is basically the range we cannot measure.
And also, what if there is in that range, but not in the terahertz range?
Yes, that is a problem. And right now we're just looking in the megahertz to a terahertz range. So that is something you can further study on yourself. Good luck.
Any more questions?
Okay, so like that's it. Thank you again, Nadia and Alan. Okay, we will take a decently brief break now until 4:30, and then we'll have some closing remarks. Thank you.
Det är inte hela världen.
aktivt. Jag vet inte, jag tror väldigt många är trötta. Jag tror ganska många har Ja. Vilken person? Den finns inspelad. Jag kan förklara den för dig. Allt för dig.
Alltså inte några problem med att man försvann. Just say it. Jag har inte varit här.
Som har fått Neil Dummies mentor är från Frankrike. Nej, det är en svensk grej, men svensk och det är ja, för väldigt många av vi forskar på universitet och väldigt många doktorander och postdoc arbetar utomlands för att forskar på universitet utomlands. Så det är fortfarande människor som kommer till Sverige för att forska. Min mentor gör parten på en gratis resa. Tyvärr så var jag upptagen på familjeresa, men det var någon konferens som göra analys relaterat till projektet som jag det är ju nästa vecka skulle man säga. Och då sa de att universitetet kunde betala flygbiljetten och boende. Nästa vecka också. Så jag behövde tyvärr tacka nej. Men vad ska du ha? Peru. 25% av världens kokain. Jag kommer tillbaka till min dag.
Ja, och så. Men
Ja, det blir nog väldigt.
Ja, alltså samma.
Kan vi börja närma oss våra platser igen så att vi kan köra lite avslutande ord. Okay. For some closing remarks, I would like to start out by saying how hard We know that each and every one of you students have worked, and we're so very proud of you. We've seen you at all hours of the day working on your project, being stressed, being not stressed, supporting each other. I think that's so incredibly important that you work together and you're incredibly generous people who never hesitate to help each other. And I think that's so amazing, and that you're all amazing people. And then to move on, apart from an audience of family and friends and mentors, etc., there has also been a jury consisting of previous RAISE students Miranda Karlsson, Antoni Kowalik, Melvin Storbacka, and Alexander Lundgren listening to the presentation. And they are now going to come up here to award the distinction of Best Presentation. Welcome to the stage, the jury.
Today we had the opportunity to listen to 15 great presentations filled with knowledge, fun, and inspiration for future research. You may all have your favorite, as you should. The students are all amazing. However, we, the panel, after thoughtful deliberation, landed on one that captured the scientific spirit. Making the complex simple, welcome to stage a well-structured and engaging talk about diapers and improving with biopolymers. Henrietta.
Congratulations, Henrietta. Good job. I'm gonna be sentimental again, reiterate how proud we are of each and every one of you. This has been an amazing month. It's incredible to see young people, not as if I'm old, but you know, to see high school students devote their summer to incredibly hard work. And you should also be very proud of yourselves. And we're now going to hand out a diploma to all of the students. So Ulla, would you please join me? We will call out your name, please come to the stage. And then when you receive your diploma, please stay on the stage for some group photos later. Okay, we're starting. Klara Bragesjö Björkén. Next up, Danny Suer. Next, Marie Brassé. Oskar Berg. Emily Liu. Allan Ismail. Henrietta Nilsson. Sofia Nordblom. Isak Karlsson. Selma Lauar. Kasper Johansson. Nadja Kuritzén. Anvi Nguyen. Benjamin Henriksson. Augusta Woltermuth Rampe. Muammar Al-Jabouri. Julina Savela. Simon Grafström. Snezhana Polishuk. Hanna André. Och sist men inte minst, Jakob Hyttner. Kan du arrangera er fint kanske?
Lyft ihop er. Alla ni är lyckliga. Kolla på mönstret.
Oj, vi är i vägen. Någon live var bra.